Great job so far. 2 courses down, 4 to go. You've already learned the basics of computing, and you just finished learning about the bits and bytes of computer networking. Now it's time to navigate the Windows and Linux operating systems, or OSs. But before we dive in, I'd like to introduce myself. We met way back in the first course. But for those of you who might have forgotten or skipped those lessons, my name is Cindy Quach, and I'm a site reliability engineer at Google. The team I work on is responsible for the management and support of Google's entire internal mobile fleet, Android OS, iOS, and Chrome OS. Before focusing on mobile, I was a systems administrator on the Linux team. And before that, I was an operations engineer. But like a lot of the Googlers you've met and will meet, I started my career as an IT support specialist. I've been working in IT for 7 years now. The first time I can remember interacting with computers was in middle school, when my teacher brought them into our classroom so we could create fun video and multimedia projects. It was my brother who brought technology into our house. My parents were immigrants from Vietnam, and we didn't have a lot of money growing up, so we had to be creative if we wanted to play with a computer at home. I can remember spending hours with my brother as he assembled a computer, and I would just ask a million questions. Eventually, I wanted to try and build my own computer, so I gathered up some old parts and saved money to buy new components. I finally put all the parts together from what I remembered my brother doing, but it didn't work out. It turns out I used some incompatible parts, but through a lot of trial and error, troubleshooting, and long search sessions on the internet, I finally got it to work. The feeling I got when I heard my computer boot up for the first time was amazing, and before I knew it, I was hooked on computers. I really enjoyed the intense concentration and problem solving required in IT, but I didn't think a career in tech was even possible back then. Once I got to college, I had to find a job to help pay for tuition, and that job was an IT support specialist on campus. That's when I realized that tech is actually something I could pursue as a career. I've been working with computers for as long as I can remember, and much of my IT knowledge was based on my own troubleshooting experiences over the years. I was great at troubleshooting issues with operating systems, or so I thought. It wasn't until I became a systems administrator on Google's Linux team that I realized just how little I knew about operating systems. I was surrounded by brilliant teammates who maintained code for large open-source operating system projects. Some even had Wikipedia pages written about them, so it was hard not to feel inadequate at times. Like I was learning to walk again as I dove more into Linux. I just wasn't used to working on the command line, and it felt overwhelming to use it to troubleshoot obscure issues that popped up. I had to constantly look up commands and figure out where to find certain files. But I didn't let it get the best of me. I took things day by day, and after a year of being on the team, I realized I had progressed incredibly far. 1 year later, I was building and packaging my own tools, then deploying them for everyone to use. I was contributing code directly to open source software. Using the command line had become second nature. There's so much to learn about operating systems, and it's one of the reasons why I'm passionate about teaching this course. Learning Linux doesn't have to be scary. It's not impossible to use Windows commands, and it's certainly not difficult to get started. So let's just do that and get started. While this course will have some conceptual learning, we'll focus more on the practical aspects of the operating system. Not only will you learn how to use the Windows and Linux OSs, we'll also teach you how to interact with these operating systems through the command line. Remember that the command line inputs text commands instead of relying on a graphical user interface, or GUI. If this is your first time using a command line for any OS, you might find this a little intimidating at first. That's totally normal. But you'll be well on your way to become a command line wizard by the end of this course. As always, we'll help guide you every step of the way. And you can always rewatch the lessons if you need to take a refresher. So take your time. You got this. We're not only going to teach you how to use the command line in Windows and Linux. You'll also learn how file systems work, and you'll be able to assign different user permissions and roles, which is a super important task in any IT support role. You'll be able to understand how to use package managers and consider the trade-offs between different package managers for Windows and Linux. We'll also teach you about process management, so you understand the nuances of running programs. That could save you valuable time when troubleshooting in the workplace. We'll also take a deeper dive into the remote connection tools you've already been using to help you access other computers when you're working at a distance. Finally, we'll teach you about OS deployment, or how to install OSs on a lot of machines at once. By the end of this course, you'll become a real OS power user in both the Windows and Linux operating systems. This is an invaluable skill set for anyone pursuing a career as an IT support specialist. After all, we spend most of our time within an operating system. But remember, you'll need to practice, practice, and practice some more to get a firm grip on operating systems. Just like with any skill, you need to really apply yourself to get good at it. Eventually, navigating the operating system will seem like second nature to you. We strongly recommend that you follow along in this course with a computer using one, if not both, of these operating systems. Navigating a real operating system while following along this course is a much more efficient way to learn these concepts. If you don't have access to them, that's totally okay. You'll be doing active learning exercises in an application called Quick Labs to help simulate what it's like to use the Windows and Linux OS. I'm super excited to teach you about Windows and Linux OSs, so let's get started. We dipped our toes in the Windows and Linux OSs in the first course of this program. Now, let's jump right in and learn how to perform all the common navigational tasks of both operating systems. For Windows, we're going to learn how to navigate the operating system using the GUI and using the command line interpreter, or CLI. For Linux, we're only going to focus on learning the command line. The command line interpreter in Linux is called a shell, and the language that we'll use to interact with the shell is called bash. It's worth calling out that these two operating systems are very similar to one another. So even if you don't know how to use the Linux GUI, as long as you know how to navigate the Windows GUI, you'll be able to apply those tools to the Linux GUI. It's possible that you'll only be using the Windows GUI in the workplace. Even so, if you learn how to use the Windows command line, this will set you apart from other IT support specialists. You'll soon discover that using the command line in any operating system can actually help you complete your work faster and more efficiently. We strongly encourage you to follow along and actually perform the tasks we do in this course yourself. If you can, pause the video and do the exercises that we do, or type out any of the commands we introduce. It will be much easier for you to understand them this way. We also recommend that you document all of the commands that we show you. Either write them down with an old-fashioned pen and paper notebook, or type them out in a doc or text editor. Chisel them on a stone if you have to. We just want you to write them down somewhere. You probably won't remember all of the commands immediately when we first introduce you to them, but with a little practice, typing the commands will become second nature to you. You can also use the official Windows CMI and Bash documentation that we've provided for you in the supplemental reading right after this video for reference, if you need to. In this lesson, the content is broken down into two themes. The first is basic operating system navigation, like navigating from one directory to another, getting file information and removing files and directories. The second theme is file and text manipulation, like searching through your directories to find a specific file, copying and pasting, chaining commands, and more. Okay, enough chit-chat. Let's get started. In operating systems, files and folders, or directories, are organized in a hierarchical directory tree. You have a main directory that branches off and holds other directories and files. We call the location of these files and directories paths. Most paths in Windows look something like this: C/users/Cindy/desktop. In Windows, file systems are assigned to drive letters, which look like C or D or X. Each drive letter is a file system. Remember that file systems are used to keep track of files on our computer. Each file system has a root directory, which is the parent for all other directories in that file system. So the root directory of C would be written C/, and the root directory of X would be written X/. Subdirectories are separated by backslashes, unlike Linux, which uses forward slashes. A path starts at the root directory of a drive and continues to the end of the path. Let's open up this PC and navigate to our main directory. The main directory in a Windows system is the drive that the file system is stored on. In this case, our file system is stored on local disk C. From here, I'm going to go to Users, then my user folder Cindy, and finally to Desktop. If you look at the top here, you can see the path I'm in. local disk, users, Cindy, desktop. That wasn't too hard, right? You can see here in our desktop directory that we have a few folders and files. We have a puppies pictures folder, a Hawaii folder, and a file called My Super Cool file. There are also some files on here that you can't see. We call these hidden files. They're hidden for a few reasons. One is that we don't want anyone to see or accidentally modify these files. They could be critical system files or configs, or even worse, embarrassing pictures of you in grade school rocking a mullet. It's okay, you aren't the first person who liked their hair to be business in the front and party in the back. Just for fun, let's see what kind of hidden files we have in here. We'll go to the top and click View. Then check the Hidden Items checkbox. Now we can see all the hidden files on our system. Oh, interesting. There's a file named Secret File. As much as I'd like to take a peek at it, whoever created it probably doesn't want us to see what's inside. So we're going to leave it alone. Let's go ahead and revert this option so we don't accidentally change something else. Okay, so what if we wanted to view information about a file? Well, to do this, we can actually just right-click and choose Properties. Let's try this for My Super Cool file. Oh, this pop-up dialog has a lot of information displayed here. Let's break it down. In the General tab, we can see the file name, the type of file, what applications we used to open it, and the location path of the file, which is C/users/Cindy/desktop. Then we have the size of the file and the size on disk. This can be a little confusing. The size of the file is actually the amount of data that it takes up, but size on disk is a little different. It's not something you need to know right now, but if you want to learn more about it, you can check out the next supplemental reading. All right, let's move on. Next, you have timestamps of when the file was created, last modified, and last accessed. After that are file attributes we can enable for our file. We have read-only and hidden. You might guess that if you check hidden, our file will be hidden and only visible if we enable show hidden items. There are some advanced options too, but we won't touch those for now. You'll also notice a few other tabs here at the top. Security, Details, and Previous Versions. We'll talk more about the Security tab in a later lesson. The Details tab basically tells us the information we just discussed about our file. The Previous Versions tab lets us restore an earlier version of a file. So if you made a change to a file and wanted to revert to that change, you could go back to that version. So to sum up listing the directories in the Windows GUI, we can see the list of files and folders by default here. You can even change how you want to view them using icons or even a list. Then if you want to get more information about a file, you can look at its properties. Next up, let's see how to view all this information through the Windows CLI. It's important to know that there are a couple of command line interfaces, or CLIs, available in Windows. The first one is called the command prompt, command.exe. The second one is PowerShell, or PowerShell.exe. The command prompt has been around for a very long time. It's very similar to the command prompt that was used in MS-DOS. Since PowerShell supports most of the same commands as command prompt, and many, many more, we're going to use PowerShell for the exercises in this module. I want to call out that many PowerShell commands that we'll use are actually aliases for common commands in other shells. An alias is sort of like a nickname for a command. The first command that we'll use is for listing files and directories. Let's start by listing the directories in the root of our C drive. The C drive is where the Windows operating system is installed. For many of you, it might be the only hard drive that you have in your computer. To get to the PowerShell CLI, just search in your Applications list PowerShell. From here, we can go ahead and launch the PowerShell program. We're going to use the ls or list directory command and give it the path of where we want to look. The path is not actually part of the command, but it is a command parameter. You can think of parameters as a value that's associated with a command. Now you can see all the directories in the root of your C drive. You might just see a few or a whole bunch of directories. It all depends on what your computer is used for. The C drive root folder is what we call a parent directory, and the contents inside are considered child directories. As you continue to work with operating systems, you'll encounter terms that may seem a bit out of place at first, but they actually make a lot of sense. Parents and children are common terms that stand for hierarchical relationships in OSs. If I have a folder named Dogs and a second folder nested within that folder called Corgi, Dogs would be the parent directory and Corgi would be the child directory. Let's look at a few of the common child directories in this folder. Program files x86. These directories contain most of the applications and other programs that are installed in Windows. Users. This contains the user profile directories or home directories. Each user who logs into this Windows machine will get their own directory here. Windows. This is where the Windows operating system is installed. If we open up PowerShell and run get-help ls, we'll see the text describing the parameters of the ls command. This will give us a brief summary of the command's parameters, but if you want to see more detailed help, try get-help ls-full. Now you can see a description of each of the parameters and some examples of how to use the command. What if we wanted to see all the hidden files in this directory? Well, we can use another useful parameter for the ls command, -force. The -force parameter will show hidden and system files that aren't normally listed with just ls. Now you can see some important files and directories, like recycle bin. This is where the recycle bin lives. When you move files to the recycle bin, they're moved to this directory instead of being deleted immediately. Program data. This directory contains lots of different things. In general, it's used to hold data for programs that are installed in program files. Alright, now that you've seen how to take a look around the file system in Windows, let's see what this process looks like in Linux. Okay, now that we know how directories are laid out, let's start moving from one directory to the next. You probably change directories in your GUI a lot without even realizing it. Even if that's not the case, we're going to go ahead and show you how to do it. Knowledge is power! There, that was pretty simple, right? We can move freely between any directory and any path on our systems. One thing to call out is that there are two different types of paths, absolute and relative. An absolute path is one that starts from the main directory. A relative path is the path from your current directory. These two distinctions aren't as important when we're working in a GUI, but they're important when you work in a shell. So let's see what this looks like in the Windows CLI. When you first open PowerShell, you'll usually be in your home directory. Your prompt shows you which directory you're currently in, but there's also a command that will tell you where you are. pwd, or print working directory, tells you which directory you're currently in. If we want to change the directory that we're in, we can use the cd or change directory command. To use this command, we'll also need to specify the path that we want to change to. Remember, this path can be absolute, which means it starts from this drive letter and spells out the entire path. On the flip side, it can be relative, meaning that we only use part of the path to describe how to get to where we want to go relative to where we currently are. I'll show you what I mean in a minute. So right now, we're in C/users Cindy. Let's say that instead I want to go to C/users/Cindy/documents. What do you think the command would look like here? Here it is. CD C/users/Cindy/documents. And now we've changed to the documents directory. We used an absolute path to get to this directory, but this can be a little cumbersome to type out. We know that the documents directory is under the Cindy folder. So can't we just go up one level to get to that folder? We absolutely can. There's a shortcut to get to the level above your current directory. CD ... Let's run the pwd command one more time. Now we can see that I'm in C/users/Cindy, the parent directory of where I was before. The ... is considered a relative path because it'll take you up one level relative to where you are. Let's go back to the Documents folder and try this again, except this time let's go to the desktop folder using the new command we learned. We know that the desktop and document directories are under the home directory, so we could run cd ... then cd desktop, but there's actually an easier way to write this. cd ... \desktop. Let's check pwd one more time. pwd now shows that we're in the desktop folder. Sweet! Another cool shortcut for cd that you can use is cd tilde. The tilde is a shortcut for the path of your home directory. Let's say I want to get to the desktop directory in my home folder. I can do something like this, cd tilde \desktop. We've done quite a bit of typing so far. You might actually be wondering what would happen if we messed up while typing these directory names. How are we supposed to memorize where everything is and if it's spelled correctly? Fortunately, we don't have to do that. Our shell has a built-in feature called tab completion. Tab completion lets us use the tab key to autocomplete file names and directories. Let's use the tab completion to get to our desktop from our home directory. If I type D and then tab, the first file or directory starting with D will now complete. Now, if this isn't the file or directory that I was looking for, I can continue to press tab and the path will rotate through all the options that complete the name that I started to type. So I'll see desktop, and then documents, and then downloads. Take note that the dot in front of the path of ./desktop just means the current directory. If I erase this and instead type DE, then the only directory that matches is desktop. Tab completion is an awesome feature that you'll be using more and more as you continue to work with commands. In Bash, the command to make a new directory is the same as in Windows. Let's make a new directory called myCoolFolder with the makedir or makeDirectory command. And now we can verify myCoolFolder is in our desktop. Instead of using backticks like in Windows to escape a character, in Bash you can use a backslash. Similar to Windows, you can also use quotes to encompass an entire file name. How do you think you would make a directory called myCoolFolder in Linux with spaces? Makedir my \cool\folder. Oh, there it is. Or makedir quotes my cool folder. Works as well. If you guess this, you're right. If you guess wrong, that's okay. Just rewatch this video so you can get a better grasp of how we came to this conclusion. Picking right up from the last video, let's say we want to make a couple of directories, mycoolfolder2 and mycoolfolder3. We could just type makedir mycoolfolder2 and then type again makedir mycoolfolder3, but instead we're going to use another cool PowerShell feature called history. Each and every time you enter in a command, it gets saved into memory and added to a special file. You can go through the previous commands you used with the history command. I'm now showing a list of commands that I entered earlier. This information alone isn't very useful. Instead, there's a better use of the history that lets us quickly scroll through these commands and use them again. We can scroll through these commands with the up or down keys on our keyboard. I'm going to go up to my previous command and I should see that I had makedir mycoolfolder. Instead of typing the whole thing to make a new folder, I'm just going to append the number 2 to my command. And boom! A new file was created without having to type everything over again. Cool, right? You can even search through your previously used commands using the history shortcut Ctrl-R. From here, you can start typing bits and pieces of the command you want to look for, and it'll show you matches. Let's search for the word folder. I should see the makedir commands I was using before. Pretty neat. If you're using an older version of PowerShell, it may not have the Ctrl-R feature. If that's the case, you can type the pound symbol followed by some part of your old command, and then use tab completion to cycle through the items in your history. The history feature, along with tab completion and get-help, will be your best friends while you work in PowerShell. Keep them close to you and get to know them super well. Our shell is looking a little cluttered. It's kind of hard to see where I'm at, so let's clean up our shell a little bit. We can do that with the clear command. This doesn't wipe your history, it just clears the output on your screen. That looks a little better. The exact same history command that's used in Windows is used in Linux. From here, we can use our up and down keys and even search through our history with Ctrl-R. To clear your terminal up, what do you think you'd do? That's right, the clear command. We've already created a few files and directories, but we need a couple more. We don't want to create them all from scratch, so let's make copies instead. In the Windows GUI, all you need to do is right-click, copy, then paste. You can also use hotkeys if you want. A hotkey is a keyboard shortcut that does some sort of task. In Windows, the hotkey for copy is Ctrl-C, and for paste, it's Ctrl-V. In PowerShell, the command used to copy something is cp. We also need to add a file that we want to copy and the path of where we want to copy it to. Let's copy mycoolfile.txt to the desktop. There you can see mycoolfile.txt was added to our desktop. I have a few of these files I want to move over, but I'm feeling a little lazy and don't want to run this command over and over again. So I'm going to use something called a wildcard to help me copy over multiple files at once. A wildcard is a character that's used to help select files based on a certain pattern. Let's say I want to get all the files that were JPEGs and copy them somewhere. I'm going to go into my Documents directory. I have files called hotdog.jpg cottoncandy.jpg, and pretzel.jpg. I need to come up with a pattern to help me select all these files. What do they have in common besides being named after delicious food? The .jpg extension. Literally anything else can be in front of the .jpg file extension and it won't matter. That's what the wildcard asterisk does. It's the pattern for anything. So I'm essentially saying select all the files with the pattern anything.jpg. So to copy over all the JPEGs in the folder, I can use cp, the asterisk symbol, .jpg, and the path I want to copy them to. Let's just verify. There it is. Now instead of copying files one by one, we can use a single command to get all the files we want. We'll talk more about other pattern expressions in the automation course. For now, the only selector we'll be using is the asterisk for all. Okay, next up, let's say I want to copy over a directory. I'm going to try to copy a folder called bird pictures to my desktop. Let's just go back into documents. Here's bird pictures. Now copy bird pictures to desktop. Now this does exactly what we told it to do. It copies the directory. However, this directory is empty. What it doesn't do is copy over the contents of the directory. To copy over the contents of a directory, you need to use another command parameter, recurse. The -recurse parameter lists the contents of the directory. Then if there are any subdirectories in that listing, it'll recurse or repeat the directory listing process for each of those subdirectories. We'll need to use the -recurse parameter with copy to copy the contents of the directory along with the directory itself. We're going to use a new parameter, verbose. Copy doesn't output anything to the CLI by default unless there are errors. When we use copy-verbose, it'll output one line for each file of the directory being copied. Let's give it a try. Copy bird pictures. And the recurse and verbose flag. This just message says that we've already copied bird pictures, but what we didn't do was copy over the file, which is now here. Excellent. Now the directory and all the contents are copied to my desktop. In Bash, the exact same Windows command can be used for copying files. Let's take a look at this directory. Let's copy my very cool file.txt to my desktop. And there it is. We can also use the same asterisk wildcard to select patterns. Since this is similar to our Windows copy command, what do you think we can use to copy over the .png files in this directory? I have files called pizza.png, soda.png, cake.png. So I can use copy *.png, then the desktop directory. Now if I look at my desktop again, there they are. The same copy rules apply in Bash if we want to copy over a directory. We have to recursively copy over the directory to get all the contents. The flag for recursive copy is -R. If I want to copy over my cat pictures folder to the desktop, I could do something like this. And there it is. We talked about making and copying files and directories so far, but what if we wanted to rename something that we created? Well, in the Windows GUI, if you wanted to rename a file, we just right-click and rename. In the command line, if we wanted to rename a file, we can use the move or move item command. It lets us rename files. Let's move the file without changing the directory that it's stored in. On my desktop here, I have blue document, and I'm going to move or rename it to yellow document. Now you can see that I have a yellow document. As you might guess, the move command also lets us move files from one directory to another. Let's move the yellow document into My Documents. And I can verify that. There it is. Cool! You can even move multiple files by using wildcards. And now you can see the rest of my colored documents went into My Documents. The exact same command can be used for Linux. mv or move can rename and move files and directories. Same thing applies here. I'm going to move my red document and rename it to blue document. Now we can see it's been renamed to blue document. Then I'm going to move the blue document into the Documents folder. There it is. Using wildcards, we can move multiple files at once, just like Windows. So let's move all the underscore document files here to our desktop. Now if we check the desktop, there they are. Alrighty, now that we've learned how to list, create, and move around files and directories, let's start removing them. In the Windows GUI, if you wanted to remove a file or folder, just right-click and delete. The file ends up in the recycle bin, which you can find on your desktop. If you wanted to restore a file here, you could just right-click and restore. If you empty your bin for any reason, you won't be able to retrieve those files. In PowerShell, the command to remove files and directories is rm or remove. Take caution when using remove because it doesn't use the recycle bin. Once the files or directories are removed, they're gone for good. Let's remove a file called text1.txt in my home directory. We can see, there it is. I'm just going to remove it. And now it's gone. The remove command might seem like a dangerous weapon in the wrong hands. Fortunately, there are safety measures in place that only give this ability to users that are actually authorized to use it. We'll talk more about file permissions in a different lesson, but let's take a quick look at what I mean. Let's remove a file called Important System File. Oh, I get an error message saying that I don't have permission to delete this file. In some cases like this one, it's because it's been marked as a system file. In other cases, it might be because I don't have enough permissions in the file system to remove the file. I do have the right permissions this time, but since it is an important file, PowerShell wants to make sure that I meant to do this. If I repeat the command with the -force parameter, remove will go ahead and remove the file. Let's take a look. -force. And you can see the file's gone. If the file belongs to someone else, or if I'm not an administrator, then I might not have the right permissions to remove the file. In that case, I'll need to access an administrator account to remove the file. Okay, let's try removing a directory with remove next. Oh, here we go. Here's another place where PowerShell is going to ask us if we really meant to do this. Since this is in a directory, it contains other files, and we did not use the -recurse parameter. We see a prompt asking us to confirm if we really want to remove the directory and all its contents. We can say yes or yes to all to continue. We can also cancel this command and run it again with the -recurse parameter. That way, PowerShell knows that we understand the consequences of what we're doing. So let's go ahead and cancel this and try again. -recurse. Yep, now it's gone. And that's the remove command in a nutshell. Again, because of the nature of this command, you'll want to be extra careful when removing files or directories. To remove files from Linux, just like in Windows, we can use the rm or remove command. Let's remove this text1 file. Just like that, it's gone. Similar to Windows, we get a message if we try to remove something that we shouldn't be able to. Let's remove this self-destruct button. Awesome, everything is working as intended. Next, let's try removing a directory. If you thought to yourself that we need to also recursively remove this directory, you'd be right. Excellent deduction skills. So rm-r, let's remove the misc folder directory. And if we check, the misc folder is now gone. Remember, when using the rm command, take extra precaution that you aren't removing something important by accident. I knew enough to be dangerous, and I think that's what got me into my systems administrator role in Linux. When I got in that role, I was working with people who were like insanely brilliant. They have Wikipedia pages written about them, about their contributions to like Linux and all these open source contributions they've done. They weren't using the operating system, they were like engineering it, they were like contributing code and fixing hardware issues and fixing software issues. That type of environment really leveled up my skills in terms of Linux because I had to learn. I had to keep up somehow, so I would read their bug reports and what they did. I guess I'd say about after a year I was really comfortable in the command line. I was packaging my own tools and I was writing code and I was contributing to like open source projects, and it was definitely an eye-opener considering like how much I thought I knew about operating systems to like what I know now. The feeling you get when you contribute code to something that thousands, if not millions of people might use, that you kind of don't believe that you just did that. But people, I mean, that's the feeling you get when you do something in the open source community. I'm passionate about operating systems because there's a lot of stuff that you can do with them. You can contribute code to an operating system like Ubuntu or Debian, and you can make an actual like impact. I mean, I can't go out and build a new CPU or something and have people use it, but I can contribute code, I can fix a bug, and you know, there's like so much stuff you can do with the operating system. It's unbelievable. Now that we've learned the basics of file and directory navigation, let's learn how we can display and edit files, search for text within files, and more. In the Windows GUI, if we want to open a file and view its contents, we can just double-click on the file. Depending on the file type, it'll open in a default application. In Windows, text files default to open in an application called Notepad. But we can change this if we want to. To change the default application that opens files, just right-click and click Properties. Under Open With, we can change the application to another text editor, like WordPad. Most of the files that we'll be dealing with throughout this course will be text and configuration files. So let's just focus on those files instead of images, music files, etc. Viewing the contents of a file in PowerShell is simple using the cat command, which stands for concatenate. Let's give it a try. This will dump the contents of the file into our shell. This isn't the best solution for a file, since it just keeps writing the content until the whole file is displayed. If we want to view the contents of the file one page at a time, we can use the more command, like this. The more command will get the contents of the file, but will pause once it fills the terminal window. Now we can advance the text at our own pace. When we run the more command, we're launched into a separate program from the shell. This means that we interact with the more program with different keys. The enter key advances the file by one line. You can use this if you want to move slowly through the file. Space advances the file by one page. A page in this case depends on the size of your terminal window. Basically, more will output enough content to fill the terminal window. The Q key allows you to quit out of more and go back to your shell. If we want to leave the more command and go back to our shell, we can just hit the Q key. Here we are. Now what if we just wanted to view part of the file? Let's say we want to quickly see what the first few lines of a text file are. We don't really want to open up the whole file. Instead, we just want to get a glimpse of what the document is. This is called the head of the file. To do this, we can go back to cat and add the -head parameter. This will show us the first 10 lines of a file. Now, what if we wanted to view the last few lines, or the tail of the file? I bet you can guess what we're going to do. This will show us, by default, the last 10 lines of a file. Again, these two commands don't seem like they have any immediate use to you yet. We'll see their benefits when we work with logs in an upcoming lesson. Now, let's take a look at how to do these same tasks in Linux. To read a simple file in Bash, we can also use the cat command to view a document. So let's look at important document. The cat command is similar to the Windows cat command since it doesn't do a great job at viewing large files. Instead, we use another command, less. Less does a similar thing that more does for Windows, but it has more functionality. Fun fact, there's a bash command called more, but it's been slowly dying out in favor of less. It's literally a case of less is more. Similar to more, when we use less, we're launched into an interactive shell. Some of the most common keys you'll use to navigate this tool are the up and down keys, page up and page down. G, this moves to the beginning of a file. You can see now we're at the beginning. Capital G, this moves to the end of a text file. Now we're at the end. slash, and then a word search. This allows you to search for a word or phrase. If I type in slash, then type the word I want to search for, I can scan through the text file for words that match my search. Q. This allows you to quit out of less and go back to your shell, similar to the Q key in the Windows More command. Do you see how less offers functionality like searching within a file? Less is a great tool to use to view files of any size. You'll no doubt end up using this command often as an IT support specialist. Similar to the Windows cat and head parameter, we can do the same thing in Linux using a command called head. This will show you, by default, the first 10 lines of a file. Now, what if you wanted to view the last few lines of a file? You can use a command called tail. This will show you, by default, the last 10 lines of a file. So far, we've discussed how to read and modify files, but we haven't covered how to edit file contents yet. Spoiler alert, you're about to learn. You can edit text-based files in Notepad, which we used earlier to view a text file. Notepad is great for basic editing, but when making changes to configuration files, scripts, or other complex text files, you might want something with more features. There are lots of good editors out there for the Windows GUI. For this demonstration, we'll use one called Notepad++. Notepad++, which you can access from the next supplemental reading, is an excellent open-source text editor with support for lots of different file types. Notepad++ can open multiple files and tabs. It also does syntax highlighting for known file types and has a whole bunch of advanced text editing features. Syntax highlighting is a feature that a lot of text editors provide. It displays text in different colors and fonts to help you categorize things differently. We've already installed Notepad++ on our machine, so you can check out their website and do the same. Now, you can edit any file using Notepad++ by right-clicking it and selecting Edit with Notepad++. What if you wanted to edit a file from the CLI? Unfortunately, there's no good default editor in the PowerShell terminal, but we can launch our Notepad++ text editor from the CLI and begin modifying text that way. So start, Notepad++, and then just a file name. Yep. As you can see, it opened up Notepad++ and asked if I wanted to create this file. If you'd like to read about text editors that you can specifically use in the CLI, check out the supplemental reading on an advanced text editor called Vim. In Linux, there are many popular text editors that we can use to modify files. We won't have enough time to cover them all, so let's just focus on one editor that can be found on virtually any distribution, Nano. Nano is an extremely lightweight but useful text editor. We've included it in the supplementary readings after this video, so go check it out. To edit a file in Nano, just type Nano, then the file name. Once we do that, we'll be launched into the Nano program. From here, we can start editing content as we normally would with any other text editor. At the bottom of the screen, you'll notice a few options like "G" and "K". The caret means to use Control-G or Control-K. We won't talk about all these options, but a few that might be useful are Control-G, which helps open up a help page, and Control-X, which is used when you want to save your work or exit from Nano. Let's go ahead and edit this file, then save our changes. It's asking me if I want to save the file or exit and discard my changes. I'm just going to hit Y because I want to save them. Once I do that, I'll be exited from Nano. Let's verify we actually changed that file. There it is. Nano is a super useful tool if you need a quick text editor in Linux. But if you want to be a true OS power user, I recommend that you read the supplemental material I've included to learn more about the text editors that are used in the industry, like Vim or Emacs. So far in this course, we've been using command aliases in PowerShell. PowerShell is a complex and powerful command language that's also super robust. We've been able to use common aliases that are exactly the same as their Linux counterparts. But from here on out, we'll need to deploy some advanced command line features, so we'll need to look at real PowerShell commands. You've already seen an example of a real PowerShell command, get-help, which is used to see more information about commands. There's another PowerShell command that we can use to look at one of our aliases that we've been using, ls or list directory. To see what the actual PowerShell command is that gets executed, we can use the PowerShell command get-alias. Interesting, when we call ls, we're actually calling the PowerShell command get-child item. It gets or lists the children, which are the files and subdirectories of the given item. Let's actually run this get-child item command with the item c, \. You'll see this is the same output as ls_c \. Cool! PowerShell commands are very long and descriptive, which makes them easier to understand. But it does mean a lot of extra typing when you're working interactively at the CLI. Aliases for common commands are a great way to work more quickly in PowerShell. We've been using them up to this point to help us hit the ground running with the command line. In Windows, you pretty much have 3 different ways you can execute commands. You can use real PowerShell commands, or the relatable alias names. Another method we've mentioned but haven't really talked about yet is command.exe commands. Command.exe commands are commands from the old MS-DOS days of Windows, but they can still be run due to backwards compatibility. Keep that in mind that they aren't as powerful as PowerShell commands. An example of a command.exe command is dir, which coincidentally points to the PowerShell command get-child item, which is also where our ls alias gets pointed to. Remember the PowerShell command get-help? Well, there's a command parameter that you can use to get help with command.exe commands. /?. Keep the difference in mind. Get-help is used for PowerShell commands like get-help ls, and /? Is used for other commands like dir /?. If I tried to use ls /? it would return nothing because the PowerShell command that ls is an alias of doesn't know how to handle the parameter /?, and vice versa. You're free to use whatever commands you feel comfortable with, but in this course, we're going to use common aliases and PowerShell commands. You've probably had to search for words in a text document before, whether it was to find and replace words or for something else. Most text editors work the same way when it comes to finding words in a document. All you need to do is Control-F to search for the word. Pretty simple, right? But what if you wanted to see if a word existed in multiple files? There are a few ways we can do this. Let's talk about the GUI options, and then we'll turn to PowerShell and learn how to search for words from the CLI. Windows has a service called the Windows Search Service. This service indexes files on your computer by looking through them on a schedule. It then compiles a list of names and properties of the file that it finds into a database. This is a time-consuming and resource-intensive process. So on many Windows servers, the search service isn't installed or is disabled. On Windows 8 and Windows 10 desktop computers, it's often enabled for files in your home directory, but not for the entire hard drive. By default, the Windows Search Service will let you find files based on their name, path, the last time they were modified, their size, or other details. But by default, you can't search for words inside the files. The Windows Search Service can be configured to search file contents and their properties. This increases the amount of time that it takes for the indexer to do its work. It's sort of like the computer is doing all of the searches that you might want to do ahead of time, and then you just have to look up the result. Let's configure the service to index file contents and see what it looks like. The settings we're looking for are in the control panel, but we can use the Start menu to find the settings we need faster. Open the Start menu and then type Indexing. You'll see the indexing options in your results of the search. Click on that. Now we want to change the settings for the User folder, which is where all the home directories are stored. Select Users and then click Advanced. Now select the File Types tab and select Index Properties and File Contents. Click OK. Now close out of the indexing options. When you do this, the Windows search service will start to rebuild the index based on your new settings. This could be super fast or it could take a while. It all depends on how many files you have and how large they are. On this system, I've already let the re-indexing complete. Now I can use Windows Explorer in my home directory to find files that have a specific word in them. Let's search for the word cow. The results turn up farm animals and ranch animals.txt. Awesome, we can see the word cow in this text file. If you don't want to use the Windows search service, we can also use Notepad++, the editor that we installed in an earlier lesson. From Notepad++, press Ctrl-Shift-F to open the Find in Files dialog. From here, we can specify what you want to find and what files you want to search. You can limit your search to a specific directory, to a specific set of file extensions, and you can even optionally replace the word with another one from here. So let's search for the word cow again, and this time I'm going to search in my home directory. Find all. Oh, there we go. Now it returns farm animals and ranch animals. If we can't or don't want to use a GUI, we can search for words within files from the command line. In PowerShell, we're going to use the SLS or select-string command to find words or other strings of characters in files. You can think of strings as a way for the computer to represent text. You'll learn more about this in our IT automation course. The select-string command lets you search for text that matches a pattern you provide. This could be a word, part of a word, a phrase, or more complicated patterns that are described using a pattern matching language called regular expressions. In that same course, you'll also learn more about regular expressions, but keep in mind that this is a really powerful capability that we're just scratching the surface of. So here, we're going to search for a word in a file in my home directory. Let's search for the word cow again. You'll see that select-string found cow, and it tells you the file and the line number where it found it. Excellent! If you wanted to search through several files in a directory, you can use pattern matching to select them. Remember the wildcard character asterisk for selecting all? We can use that here as well. Now we can see that it found farm animals and ranch animals. Select-string can do lots of other things too. We'll get a chance to see that in later lessons. Being able to find a string in a file or a set of files is going to be a critical skill for you in this course and in your IT support work. It's also an important tool that we're going to learn to combine with other tools to do really powerful things from the CLI. What if we wanted to search for something within a directory, like looking for just the executables in that same directory. This is where the command parameter -filter comes in. I'm just going to ls my programs files here with the -recurse and -filter and look for exes. Wow, that's a lot of exes. The -filter parameter will filter the results for file names that match a pattern. The asterisk means match anything, and the .exe is the file extension for executable files in Windows. So the only results we're going to get are the files that end in .exe. Cool! In Bash, we can search for words within files that match a certain pattern using the grep command. What if you wanted to know if a certain file existed in a directory or if a word was in a file? Similar to the PowerShell select-string command, we can use the grep command in Bash. Let's search for the word cow in farm animals. You'll see that grep found cow in the text file farm animals. You can also use grep to search through multiple files. Let's use the asterisk wildcard command here. And you can see that it found cow in farm animals and ranch animals. You'll be using grep a lot throughout this course and in later courses, so it's an important command to remember. Alright, we've learned a bunch of individual, very powerful tools. These are the most important day-to-day commands that you'll need to work in PowerShell. Now we're going to learn how to combine these tools to make them even more powerful. Let's run the following command in our desktop directory, and then we'll break it down piece by piece. Just going to cd into my desktop directory. Okay. Echo woof dog.txt. I'm going to do an ls to check our desktop. And we'll now see a file called dog.txt. Inside that file, we should see the word woof. Oh, there it is. What's happening here? Let's take a closer look. Echo woof. In PowerShell, the echo is actually an alias for write-output. That gives us a clue to what's happening. We know the echo command prints out our keyboard input to the screen. But how does this work? Every Windows process and every PowerShell command can take input and can produce output. To do this, we use something known as I/O streams, or input-output streams. Each process in Windows has 3 different streams: standard in, standard out, and standard error. It's helpful to think of these streams like actual water streams in a river. You provide input to a process by adding things to the standard in stream, which flows into the process. When the process creates output, it adds data to the standard out stream, which flows out of the process. At the CLI, the input that you provide through the keyboard goes to the standard in stream of the process that you're interacting with. This happens whether that's PowerShell, a text editor, or anything else. The process then communicates back to you by putting data into the standard out stream, which the CLI writes out on the screen that you're looking at. Now, what if instead of seeing the output of the command on the screen, we wanted to save it to a file? The greater than symbol is something we call a redirector operator that lets us change where we want our standard output to go. Instead of sending standard out to the screen, we can send standard out to a file. If the file exists, it'll overwrite it for us. Otherwise, it'll make a new file. If we don't want to overwrite an existing file, there's another redirector operator we can use to append information, greater than, So let's see that in action. Echo woof greater than dog.txt. Now if I look at my dog.txt file again, we can see that woof was added again. But what if we wanted to send the output of one command to the input of another command. For this, we're going to use the pipe operator. First, let's take a look at what's in this file. Cat words.txt. Look at that, it's a list of words. Now what if we want to just list the words that contain the string st? We could do what we've done before and just use select-string or SLS on the file directly. This time, let's use the pipeline to pass the output of cat to the input of select-string. So cat words.txt pipe select-string st. And now we can see a list of words with the string st. To tie things together, we can use output redirection to put our new list into a file. So now, greater than, and then a new file called stwords.txt. Now if I cat stwords.txt, yep, there it is. That's just a very basic example of how you can take several simple tools and combine them together to do complex tasks. Okay, now we're going to learn about the last I/O redirector, standard error. Remember when we tried to remove a restricted system file earlier and we got an error that said permission denied? Let's review that once more. This time I'm going to remove another protected file. rm secure file. We see errors like we're supposed to, but what if we didn't want to see these errors? Turns out we can just redirect the output of error messages in a different output stream called standard error. The redirection operator can be used to redirect any of the output streams, but we have to tell it which stream to redirect. So let's type rm secure file to greater than errors.txt. If I look at errors.txt, I can see the error message that we just got. So what does the to mean? All of the output streams are numbered. 1 is for standard out, which is the output that you normally see, and 2 is for standard error, or the error messages. Heads up, PowerShell actually has a few more streams that we aren't going to use in this lesson, but they can be redirected in the same way. You can read more about them in the supplemental reading right after this video. So when we use to greater than, we're telling PowerShell to redirect the standard error stream to the file instead of standard out. What if we don't care about the error messages, but we don't want to put them in a file? Using our newly learned redirector operators, we can actually filter out these error messages. In PowerShell, we can do this by redirecting standard error to $null. What's $null? Well, it's nothing. No, really. It's a special variable that contains the definition of nothing. You can think of it as a black hole for the purposes of redirection. So let's redirect the error messages this time to $null. rm secure file to greater than $null. Now our output is filtered from error messages. There's still much more to learn if you're interested. Try get-help about_redirection in PowerShell to see more detail. It may take a little time to get the hang of using redirector operators. Don't worry, that's totally normal. Once you do start to get used to them, you'll notice your command foo skills level up and your job becomes a little easier. Now let's take a look at output redirection in Linux. Similar to Windows, we have 3 different I/O or input-output streams: standard out, standard in, and standard error. Remember the standard out example in the last lesson? Well, the same concept applies in Linux. We echo the text woof here, but instead of sending it to our screen by default, we're going to redirect the output to a file using the standard out redirector operator. Let's verify. Yep, there it is. This overwrites any file named dog.txt with the contents woof. If we don't want to overwrite an existing file, we can use the append operator, or greater than. So echo woof dog.txt. We could verify that. There it is. One redirector operator that we talked about in the Windows lesson but didn't show up an example of was the standard in redirector operator. The standard in redirector is denoted by a less than sign. Instead of getting input from the keyboard, we can get input from files, like this. This command is exactly the same as cat file input. The difference here is that we aren't using our keyboard input anymore. We're using the file as standard in. Standard in redirectors have more practical uses in scripting, but we'll get to that in Course 5 of the program, IT Automation. Until then, we can't really see their true potential. Finally, similar to Windows, the last redirector operator we'll talk about is standard error. Standard error displays error messages, which you can get by using the to greater than redirector operator. Just like Windows, the to is used to denote standard error. So to redirect just the error messages of some output, you can use something like this. ls dir vector to error output.text. Now if I view that new document, now we can see the error message in error output.text. Remember the $sign null variable that we used in Windows to toss unwanted output into a metaphorical black hole? We have something like that in Linux too. There's a special file in Linux called the /dev/null file. Let's say we want to filter out the error messages in a file and just want to see standard out messages. We could do something like this. Now our output is filtered from error messages. Remember how we talked about taking the output of one command and using it as the input of another command with the Windows pipeline? Well, the same thing exists in Linux. The pipe command allows us to do this. Let's say we want to see which subdirectories in the /etc directory contain the word Bluetooth. We can do something like this. We're using the pipe redirector to take the output of ls-la/etc and pipe or send it to the grep command. Now, without even looking through the directory, we're able to quickly see if the Bluetooth directory is in here. There it is. You've gotten a glimpse of the power of redirectors, and as you dive deeper into the world of Linux, you'll be using them on a regular basis. They're super valuable tools to have, and now they're part of your toolkit. You've learned a lot of commands and tools to help lay a strong foundation for IT support work. There are many other commands that you haven't seen yet. Don't worry, we'll get to them as they come up. As you advance in your career, you might even discover that the tools and commands you're using aren't powerful or efficient enough anymore. Maybe you'll want to search through files using more complex patterns. To do that, you'll need to know about tools like regular expressions. Regular expressions are used to help you do advanced pattern-based selection. We'll talk about this in the IT Automation course later on in this program. There's also so much more to PowerShell. There are excellent videos and articles that can guide you from the first steps you've learned here to being a Windows CLI master. If this sounds interesting to you, we really encourage you to check out the supplementary reading right after this video. And no, we won't grade you on your knowledge of this material in these courses, but it could be really useful to you in the IT support field. You've done some seriously awesome work. We've covered a lot of information in this lesson. Maybe this was the first time you've been exposed to Linux or Windows. If so, you've already passed a huge milestone in your learning journey. It's super important that you're able to use the commands you learned here by memory. I hope you wrote them down in your notes while watching the videos in this course. Next up, we'll be testing you on some of the new commands you learned in Bash and Windows CLI. Make sure to rewatch the videos and practice the exercises if you want a refresher before you start. When you're ready, we'll see you in the next lesson.
I have to say, I think that looking back, I've been really lucky. I had started off, even before I was a teenager, teaching myself about computers without even access to them. And somehow, kind of, in the end of that era, when I was an early teen, I managed to convince a bookstore owner that he needed to buy a computer, and I would program it for him to automate his textbook business. So I had never actually done that before, right? I had never laid my hands on that kind of computer before. I had never written a program like that before. And the guy believed me, and he did it, and he hired me, and I spent, that was a part-time job that stuck with me actually until I was in my mid-20s. So for like 11 years, I had this part-time job automating the textbook business of a neighborhood bookstore. And the thing that's so amazing, that I'm so grateful for, is that this guy had this faith in me and put this trust in me. And then I'm even more amazed that it actually kind of worked out, right? And I spent all those years doing it, and it helped their business and all that. But it was a great experience, and it was a great way to kick off my actual early career as a professional programmer.
Welcome back. Now that we've learned how to navigate around the Windows and Linux operating systems, let's start setting up our computer for use by other people. As an IT support specialist, you'll be responsible for other people's machines. People will depend on you to help set up their machines, troubleshooting their issues, and so on. In this lesson, you'll learn how to manage multiple accounts on one machine. You'll also learn about the different permissions and access types, how to add and remove users, and the best practices to use when managing multiple users. It's common for a computer to have multiple users. On your home computer, you might have your parents, siblings, or children using the same computer. Your town, library, school, or other public places might also have computers with multiple users. Even though these machines have multiple user accounts on them, all users on a computer are isolated from others. This means that Kevin can't see Victor's files and folders, and vice versa. There are two different types of users: standard users and administrators. A standard user is one who is given access to a machine, but has restricted access to do things like install software or change certain settings. An administrator or admin is a user that has complete control over a machine. They can view anyone's account, change and remove anyone on the computer, and view every single file. You can have multiple administrators on a machine as well. On your personal machine, you're the default administrator because this gives you complete control over your system. After all, it is your machine. But on a public computer, the administrator is someone who actually runs and maintains the machine, like an IT support specialist. They can grant access for other users, install software, change restricted system settings, and perform other actions they deem appropriate. How terrible would it be if anyone who is using a public computer could just install software? The computers would be bloated, things would be out of place, and worst of all, they could be infected with malicious software. Users are put together in groups according to levels of access and permissions to carry out certain tasks. These tasks depend on what the computer's administrator considers appropriate. An administrator could give different access and settings based on the type of group a user is in. Let's say you're an administrator for your home computer, which everyone in the house uses. You put your parents in a group called parents, and your kids in a group called children. You don't want either of them to be able to install software, but you also want to add child safety restrictions on the children group. As the administrator, you're able to specify different permissions for both of these groups. So how do you differentiate what type of user you are and what groups you're in on Windows and Linux? Well, hopefully you'd know this if you're an administrator of a computer, but if you don't, computers do a pretty good job of telling you. In the next few lessons, we'll see how we can view user and group information in Windows and Linux. To view user and group information in Windows, we're going to use the Computer Management tool. If we search Computer Management in our application search and open it up, we'll see a window that gives us a lot of information. We'll be using this application a lot throughout this course, so let's take some time to go over it. At the top of the sidebar, you'll see it says Computer Management Local. This means we're managing a single machine locally. In an enterprise environment, you can manage multiple machines in something called a domain. A Windows domain is a network of computers, users, files, etc. that are added to a central database. If you're an admin of that domain, you can view those accounts and computers from any machine in the domain. We'll learn more about domains and how to manage them in our next course on system administration and IT infrastructure services. Underneath this menu, we have System Tools. Let's do a rundown of each of these submenus. Task Scheduler. This lets you schedule programs and tasks to run at certain times, like automatically shutting off the computer at 11 p.m. every night. Event Viewer. This is where our system stores its system logs. We'll do a deep dive on this tool in an upcoming lesson. Shared Folders. This shows the folders that different users on the machine share with each other. Remember how we said that other users can't view anyone else's files? That's not exactly true. If users store files on a shared folder, anyone who has access to that folder can view it. Local Users and Groups. This is where we'll be doing our user and group management. Performance. This shows monitoring for the resources of our machine, like CPU and RAM. Device Manager. This is where we go to manage devices to our computer, like our network cards, sound cards, monitors, and more. Under the Storage menu, we have a submenu for Disk Management. We'll use this when we talk about disks in a later lesson. Finally, the Services and Applications menu shows us the programs and services that we have available on the system. We can choose to enable or disable services like DNS here. All the essential settings that we as administrators need to change are found in the Computer Management tool. If you're a power user, it's more efficient to use this than it is to go through the default settings application. Okay, let's get back to the task at hand. Let's see what kind of user account we have and what groups we're a part of. Let's go back to the local users and groups. Under Users, we can see a few built-in Windows accounts like Guest and Administrator. The local administrator account lets you log in using the administrator username and whatever the administrator password is on the computer. This account is disabled by default. Since this account has unfettered access on the computer, it can be dangerous to be logged into it at all times. For now, let's look at the account I'm in, Cindy. Let's double-click on this to see more information. Okay, let's do a rundown here. Under the tab General, we can see some basic information about the user along with some options. User must change password at next logon. Since I'm an admin, I can force other users to change their password. This is useful if I'm managing someone's account and their password was compromised. We don't want to risk someone else logging into their account, so we force them to change their password. User cannot change password. Password never expires. Account is disabled. Enabling or disabling an account means making it active or inactive. Account is locked out. This means a user account will not be able to log in. Maybe a disgruntled employee is looking to do malicious things. We can make it so that they won't be able to log into their computer. Under the Member Of tab, we can see which groups we're part of. I can see that I'm in the Administrators group. Heads up that instead of being logged into the local administrator account all the time, you can be logged into your own account and use administrative powers when you need to. This is thanks to the help of UAC, or User Access Control. This is a feature in Windows that prevents unauthorized changes to a system. These changes have to be approved by an administrator instead. Since I'm an administrator, all I would do is enter in my password to confirm that I want to make a change. Finally, on the last tab, Profile, you can change settings about your user profile, like where you want your home folder to be. This isn't terribly important on a local account, but it comes in handy when you're managing many users on a domain. Now, if we go to the Groups menu in the sidebar, it should look familiar. Just like the Member tab, we can view which groups are available and who their members are. And that's how you view user and group information using the Windows GUI. Next, let's take a look at how to do the exact same thing using Windows CLI. We talked about using the CLI in depth in the last module. We've seen how it can make our tasks quicker when we modify files and folders. Now, we're going to start using commands to help us with other tasks on our system. Imagine you're working as an IT support specialist at a company and your boss asks you to check all the user information on 10 machines to make sure that the local administrator account is not enabled. Sure, you could search computer management in the search bar, click computer management local, look under system tools, click on local users and groups, then double-click on the username of the computer to ensure that the local administrator account isn't enabled. Now you just have to do that 9 more times. There's a much faster way. You can just use the CLI to quickly see the list of users on the computer using the command get-local user. As you can see, it lists my user account, a few other users, and a couple of other default accounts that are part of Windows. Here you can see that my local administrator account isn't enabled. That's way easier. What about groups? I bet you can guess. Get-local group will list the groups on the local machine. There are a whole bunch of groups, but don't worry, these are all built-in groups. Each of them are important, but we aren't likely to make changes to most of them. One that we will make changes to is the administrators group. Remember, this group controls who has administrative access to the machine. It's important to know who's in this group, since anyone in this group can make any change they want to the machine. We just saw in the GUI that we're in this group, but I wonder who else is. Let's see who's in this group with get-local group member. And I want to check the administrators group. Okay, we can see that the administrator user and my user are in the administrators group, but no one else. Looks good to me. One last note, these local user and group PowerShell commands require that you're running PowerShell 5.1 or newer. You may have noticed that I keep saying local accounts and local users. If your organization has a lot of Windows machines, it's very common to use Active Directory to manage user accounts in a central directory service. We'll learn more about Active Directory accounts in our next course on System Administration and IT Infrastructure Services. But let's focus on local accounts for now. In Linux, user management and access works just like it does in Windows. Different user types have different privileges, and they can be grouped together with various access levels. There are a few differences in how Linux does labeling, though. There are standard users, and there are also administrators in Linux. But there's also a special user called the root user. Don't get this confused with the root directory or /. The root user is the first user that gets automatically created when we install a Linux OS. This user has all the privileges on the OS. They're the super user. There's technically only one super user or root account, but anyone that's granted access to use their powers can be called a super user too. Now, let's try and view the contents of a root restricted file. The file path is etc sudoers. Oh, we're getting an error. cat/etc/sudoers permission denied. The sudoers file is a protected file that can only be read by root. We can log in as root and then run this command, no problem, but it can be really dangerous to always be in root. Since root, like our local administrator account on Windows, has unrestricted access on the machine. If we make even one mistake, we could delete or modify something important, and that's not good. So instead of logging in as root, we can tell the shell that we want to run this one command as root. Sounds similar to the Windows UAC feature? That's because it is. On Linux, we can do this with the sudo command or super user do. So sudo cat etc sudoers. And now we're able to see the contents of this file. If you don't want to run sudo every time you need to run a command that requires root privileges, you can just use the su command or substitute user. This will allow you to change to a different user. If you don't specify a user, it defaults to root. Now you can see my prompt says root at Cindy-NYC. Again, it's generally not a good guideline to stay logged in as root all the time. There are lots of critical services and files that can be mistakenly changed. If you need to log in as root, it's okay, but just be careful. I'm just going to go ahead and exit out of root for now and go back to my normal user. You can view who has access to run sudo by viewing the /etc/group file. This is also how you view memberships for all groups. This looks a bit different from the Windows GUI, but you can see there are some similarities to the Windows CLI. It's actually pretty simple to read this file, even if you're not a Bash expert yet. Each line represents a different group. Let's look at the sudo line. There are 4 fields here separated by colons. The first field is the group name. In this case, it's sudo. The second field is the group password. We don't really need to specify a group password, so it defaults to the root password. The X here means that the password has been encrypted and stored in a separate file that we'll talk about in a later lesson. The third field is the ID of the group, or group ID. When our operating system runs a task that involves a group, it uses a group ID instead of a group name. And finally, the last field is a list of users in the group. What if we wanted to view the users on our machine? What do you think the file would be that stores that information? Unfortunately, it's not /etc/user. The file that contains user information is /etc/password. Oh wow, there's a lot more information in here, and a lot more users. Most of these accounts aren't actually humans using the computer. There are a bunch of processes that are constantly running on our computer that we need to associate with the user. So our system has lots of users with different permissions that are needed to run these processes. Let's look at this first line here, which is an actual user we can log into, root. We won't talk about all the fields since they aren't important, but the first 3 are relevant. The first field is the username, and the second field is the user password. The password isn't actually stored in this file. It's encrypted and stored in a different file, just like our group ID password. The third field here is the user ID, or UID. Similar to group IDs, user IDs are how our system identifies a user, not by the username. Root has a UID of 0, and that's basically how you view users and groups in Linux. In this video, we're going to talk about an important part of having users on a machine, and that's working with passwords. Passwords add security to our user accounts and machines. They make it so that only Marty knows the magic secret to access her account and no one else's, not even the admin of the computer. When setting up a password, you want to make sure that you and only you know that password. Remember, if you're managing other people's accounts on a machine, you shouldn't know what their password is. Instead, you want the user to enter the password themselves. To reset a password in the GUI, let's go back to our computer management tool. Under local users and groups, we're going to right-click on a username, like this account, Sarah. Let's click on Properties. And then from here, we're just going to check this box that says, User must change password at next logon. And I'm going to apply and hit OK. Then, when the user logs into the account, they'll be forced to change their password. If they forgot their password, you have the option to set a password for them manually by right-clicking and selecting Set Password. This has some caveats though, like losing access to certain credentials. You can read more about this option in the supplemental reading right after this video. To change a local password in PowerShell, we're going to use the DOS-style net command. There's a native PowerShell command that can be used to set the password, but it's a little more complicated. It requires a bit of simple scripting to use. And we'll cover scripting in the IT automation course, so if you want, you can come back to this after Phelan covers that. If you want to read ahead, you can check out the documentation for set-local user. But for now, we'll stick to the simpler, though less powerful, net command. Net does lots of different things. Changing local user passwords is just one of them. If you want to learn more about what the net command can do, take a look at the documentation in the supplementary reading for the command. Since this is an old DOS-style command, you can also use the /? parameter to get help on the command from the CLI. To change a password for a user, the command is net user, then the username and password. The best way to use this command is to use an asterisk instead of writing your password out on the command line. If you use an asterisk, Net will pause and ask you to enter your password, like so. Why is this approach better? Imagine you're changing your password, and right at that moment, someone walks behind you and glances over your shoulder. Your password isn't a secret anymore. You should also know that in many environments, it's common that the commands that folks run on the machines they use are recorded in a log file that's sent to a central logging service. So it's best that passwords of any kind are not logged in this way. Do you notice a problem with the asterisk approach, though? That's right. If I change passwords for someone else using this command, I would know their password, and that's not good. Instead, we're going to do what we did in the GUI and force the user to change the default password on their next logon using the /logonPasswordChangeYes parameter. So I'm just going to force Victor to change his password on the next logon. So net user Victor /logon password change yes. The /logon password change yes parameter means that the next time that Victor logs into this computer, he'll have to change his password. Sorry, Victor. To change a password in Linux, all you need to do is run the passwd or password command. Let's try changing my password. When you set a password, it's securely scrambled, then stored in a special privileged file called /etc/shadow. This file can only be read by root to keep away prying eyes. Even if you did have access, you wouldn't be able to descramble passwords found in here. If you're managing a computer and you want to force a standard user to change their password, like we did in Windows, you can use the -E or expire flag with password, like this. This will immediately expire a user's password and then make them set a new password the next time they log in. To add a new user in Linux, you can use the user add command. So sudo user add Juan. This will set up basic configurations for the user and set up a home directory. We can verify that Juan was created. There. You can combine this with the password command to make the user change their password on login. To remove a user, you can just use sudo user delete Juan. He's no longer on the list. Nice work! Next, we'll dive into the wonderful world of permissions. See you there!
I'm Ben Freed. I'm Google's Chief Information Officer, and I'm a Vice President of the company. I lead a team that's responsible for the technology that Googlers use to get their work done. And that could be things like the laptop and phone that you use, or the video conferencing that you use in a conference room, or the phone on your desk maybe, but it's also all the software that Googlers use every day in their work. I spend an awful lot of time actually in meetings, mostly meeting with my teams, trying to understand what they're doing and what I as a leader can do to help them. Then I spend a lot of time also talking to our customers, people inside the company, so I can understand what my teams need to do and how we can better do our work. You know, when I came and joined Google, the team that I led, it needed a lot of help. And it was a huge challenge for me to figure out what I needed to do as a leader to help them. And I just remember at one point realizing, you know, if I keep on showing up and just keep on putting in the effort every day, we'll get through this. In spite of how hard it was, and in spite of the fact that I would leave work thinking, I have no idea how I'm going to solve this problem or that problem or whatever it was. Eventually, showing up worked. Being too stubborn and too stupid to know when to quit was actually what led to me succeeding in an incredibly challenging situation.
File permissions are an important concept in computer security. We only want to give access to certain files and directories to those who need it. While we think about how we want users to access files and folders, we should also think about how the concept of permissions carries over to other areas of your life. Maybe you've locked down your social media posts to only people you trust, or given a copy of your house key to a relative in case of an emergency. You'll learn more about security principles in the last course of this program. For now, we're going to focus on one small building block, file permissions. In Windows, files and directory permissions are assigned using access control lists, or ACLs. Specifically, we're going to work with discretionary access control lists, or DACLs. Windows files and folders can also have System Access Control Lists, or SACLs, assigned to them. SACLs are used to tell Windows that it should use an event log to make a note of every time someone accesses a file or folder. This is a more advanced topic which you can read up on in the next supplementary reading. You can think of a DACL as a note about who can use a file and what they're allowed to do with it. Each file or folder will have an owner and one or more DACLs. Let's take a look at an example. In Windows Explorer, I have opened up my home directory. If we right-click on Desktop and select Properties, we can see the Properties dialog for our desktop directory. Then if we go to Security tab, we can see the Permissions window here. The top box contains a list of users and groups, and the bottom box has a list of the permissions that each user or group has been assigned. What do each of these permissions do? It changes a bit depending on whether the permission is assigned to a file or a directory. Don't worry, it'll all make sense soon. Let's do a rundown of these permissions. Read. The read permission lets you see that a file exists and allows you to read its contents. It also lets you read the files and directories in a directory. Read and execute. The read and execute permission lets you read files, and if the file isn't executable, you can run the file. Read and execute includes read, so if you select read and execute, read will automatically be selected. List folder contents. List folder contents is an alias for read and execute on a directory. Checking one will check the other. It means that you can read and execute files in that directory. Write. The write permission lets you make changes to a file. It might be surprising to you, but you can have write access to a file without having read permission to that file. The write permission also lets you create subdirectories and write to files in the directory. Modify. The modify permission is an umbrella permission that includes read execute, and write. Full control. A user or group with full control can do anything they want to the file. It includes all of the permissions of modify and adds the ability to take ownership of a file and change its ACLs. Now, when we click on my username, we can see the permissions for Cindy, which show that I'm allowed all of these access permissions. If we want to see which ACLs are assigned to a file, we can use a utility designed to view and change ACLs called iCACLs or improved change ACLs. Let's take a look at my desktop first. So iCACLs, desktop. Well, that looks useful, but what does it mean? I can see the user accounts that have access to my desktop, and I can see that my account is one of them. But what about the rest of this stuff? These letters represent each of the permissions that we talked about before. Let's take a look at the help for iCACLs. I bet that'll explain things. So iCACLs /?. All right, there's a description of what each one of these letters means. The F shows that I have full control of my desktop folder. iCACLs calls this full access, and we saw this in the GUI earlier as full control. These are the same permission. What do these other letters mean? NTFS permissions can be inherited, as we saw from the iCACLs help. OI means object inherit, and CI means container inherit. If I create new files or objects inside my desktop folder, they'll inherit this DACL. If I create new directories or containers in my desktop, they'll also inherit this DACL. If you'd like to understand more about ACL inheritance in NTFS, check out the next supplemental reading. As we've now learned, there are files and folders that have different permission sets on them so that unwanted eyes can't view or modify them. There are 3 different permissions you can have in Linux. Read. This allows someone to read the contents of a file or folder. Write. This allows someone to write information to a file or folder. And execute. This allows someone to execute a program. Let's take a look at this with the ls command. We'll use the long flag so we can see the permissions on the file. Okay, the first thing we see in this column is -rwx rw-r-. There are 10 bits here. The first one is the file type. In this example, dash means that the file we're looking at is just a regular file. Sometimes you might see D, which stands for a directory. The next 9 bits are our actual permissions. They're grouped in trios or sets of 3. The first trio refers to the permission of the owner of the file. The second trio refers to the permission of the group that this file belongs to. The last trio refers to the permission of all other users. The R stands for readable, W stands for writable, and X stands for executable. Like in binary, if a bit is set, then we say that it's enabled. So for our permissions, if a bit is a dash, it's disabled. If it has something other than a dash, it's enabled. Permissions in Linux are super flexible and powerful because they allow us to set specific permissions based on our role, such as an owner, in a group, or everyone else. Let's take a look at this in detail. The first set of permissions, RWX, refers to the permission of the user who owns that file. In this case, it's Cindy, who you can see in the owner field of ls-l. So it says here that the owner of the file can read, write, and execute this file. The next set of permissions are group permissions. We can see the group this file belongs to is the cool group. They have read and write permissions, but not execute permissions. And lastly, the permissions for all other users and groups only allow them to read this file. And that's Linux permissions in a nutshell. It might take some time to get used to reading permissions. Don't worry, you'll eventually get the hang of it. As always, feel free to review this lesson again if you need a refresher. Now that we can read permissions, let's take it a step further and learn how to change permissions in Windows. Let's say I want to give access to another person in my family to view a folder with family pictures on the computer. How would I do that? On my local disk C, I have a folder called Vacation Pictures that I want to share with another user on my machine, Devin. To do that, I'm going to right-click on this folder, then go to Properties, then the Security tab. Now I can see an option to edit file permissions. I'm going to click on that. From here, I can see that I can add a group or usernames to this ACL. I'm going to go ahead and click Add. From here, it asks me to enter the username of the person I want to add on this ACL. I'm going to enter Devin and then click Check Names to verify that I typed it in right. After it's been verified, I'm going to click OK. Once Devin's added to the ACL, I can click on his username, then check the Allow boxes for the permissions I want to give him. Let's give Devin Modify access so he can add pictures to this folder too. That's it. We've kind of been glossing over this other checkbox here, Deny. You might have already guessed that Deny doesn't allow you to have a certain permission, but it's special because it generally takes precedence over the Allow permissions. Let's say Devin is in a group that has access to this folder. If we explicitly check the Deny box for Devin's username, even if the group has access to the folder, Devin won't. Sorry, Devin. If you want to learn more about permission precedence, you can check out the supplemental reading. To modify a permission in the CLI, we're going to return to the iCackles command. In the examples I'm going to show you, we'll be running iCackles from PowerShell. The iCackles command was designed for the command prompt before PowerShell, and its parameters use special characters that confuse PowerShell. By surrounding iCackles parameters with single quotes, I'm telling PowerShell not to try and interpret the parameter as code. If you run these commands in command.exe, you'll need to remove the single quotes for them to work. So let's look at this side by side with PowerShell.exe and command.exe. In PowerShell, the command would be iCackles vacation pictures /grant with single quotes, everyone OI CI R. In command prompt, the command would be iCackles with double quotes, vacation pictures grant everyone OI CI R. We're going to see what this command does in just a moment. For now, let's take a look at the difference in the quotes. In the PowerShell example, we add single quotes to make PowerShell ignore the parentheses, and because there's a space in the path. In the command.exe example, we have to use double quotes for the path, and we don't need the single quotes anymore to hide the parentheses. Got it? Great. Now, let's take a look at the permissions that we just gave to Devin with iCackles. Cool! I see there's a new DACL attached to the Vacation Pictures directory for Devin that gives him Modify access. we can see that any new files or folders that get created in vacation pictures will be inherited. Okay, so let's say we want anyone with permission to use this computer to be able to see these pictures. We don't want them to add or remove photos though. What permissions do we want to give them? That's right, we want to give them read permission to the Vacations Pictures folder. Let's use the special group Everyone to give read permissions to the directory. So I cackles see vacation pictures / grant everyone OICIR. Success! The Everyone group includes, well, everyone. It includes local user accounts like Cindy and Devin. Guest users. This is a special type of user that's allowed to use the computer without a password. Guest users are disabled by default. You might enable them in very specific situations. Now anyone who can use this computer can browse the photos that Devin and I have put together. Actually, maybe I didn't really want everyone to look at my vacation photos. Maybe I just want the people that have passwords on the computer to be able to see them. In that case, I want to use Authenticated Users group. That group doesn't include guest users. So first, let's add a new DACL. I cackles see vacation pictures grant authenticated users OICIR. Success! Now let's remove the permissions for the Everyone group. I cackles see vacation pictures remove then everyone. Success! Now let's use iCackles to verify that the permissions are set the way we intended. iCackles see vacation pictures. Sweet! We can see that authenticated users were added and everyone is removed. Next, let's take a look at modifying permissions in Linux. In Linux, we change permissions using the chmod or change mode command. First, pick which permission set you want to change. The owner, which is denoted by a U, the group the file belongs to, which is denoted by a G, or other users, which is denoted by an O. To add or remove permissions, just use a plus or minus symbol that indicate who the permission affects. Let's take a look at some examples. So let's chmod U plus X my cool file. This command is saying that we want to change the permission of my cool file by giving executable or X access to the owner or U. You can do the same thing if you wanted to remove a permission. So chmod U minus X my cool file. Instead of a plus, we just minus. Pretty simple, right? If you wanted to add multiple permissions to a file, you could just do something like this. This is saying we want to add read and execute permissions for the owner of my cool file. And you can do the same for multiple permission sets. You could do chmod ugo plus r my cool file. Now this says we want to add read permissions for our owner, the group the file belongs to, and all other users and groups. This format of using RWX and UGO to denote permissions and users in chmod is known as symbolic format. We can also change permissions numerically, which is much faster and simpler, and lets us change all permissions at once. The numerical equivalent of RWX is 4 for read or R, 2 for write or W, and 1 for execute or X. To set permissions, we add these numbers for every permission set we want to affect. Let's take a look at an example. The first number 7 is our owner's permission, the second number 5 is our group permissions, and the third number 4 is the permission for all other users. Wait a minute, where are we getting 5 and 7? Remember, you have to add the permissions together. If you add 4, 2, and 1 together, you get RWX, which equals 7, so our owner permission is able to read, write, and execute this file. Can you guess what 5 would stand for? That's right. 4 plus 1 is read and execute. So now you can see how numeric format is quicker than symbolic format. Instead of running something like this, we can run chmod 754, my cool file, to update them all. Either way, you can change permissions using the symbolic or numerical format. Just pick whichever is easiest for you. You can also change the owner and the group of a file. The chown or change owner command allows you to change the owner of a file. Let's go ahead and change the owner to Devin. Awesome. Now Devin is the owner of this file. And to change the group a file belongs to, you can use a chgroup or change group command. Awesome. Now the best group ever is the group owner for this file. It may take a while for you to get the hang of reading and changing permissions. You can practice changing the permissions on a few files until you get it down. Permissions are an essential building block to computer security, and you'll be using them throughout your work as an IT support specialist. You might have noticed that when we were looking at permissions in the GUI before, there's a checkbox in the permission list for special permissions. The permissions that we've been looking at and setting so far are called simple permissions. Simple permissions are actually sets of special or specific permissions. For example, when you set the read permission on a file, you're actually setting multiple special permissions. Let's take a look at the list of special permissions available. I'm going to click on the Advanced tab under my permissions setting. When I click on a username and then go to Advanced Permissions, I can see a list of all the special permissions enabled on that file. When we select a basic permission like read, we're actually enabling the special permissions list folder /read data, read attributes, read extended attributes, read permissions, and synchronize, which are just fine-tuned permissions. You can modify these permissions like you would any other basic permission. Feel free to read more about the different types of special permissions in the supplemental reading I included after this video. In most cases, the simple permissions are going to be all that you need. But sometimes you need to create a file or folder that doesn't quite follow a simple pattern. Let's take a look at an example in the CLI. To view special permissions on a file in the CLI, we will simply use the iCackles command as before. Let's take a look at a more interesting example than my desktop folder. iCackles C Windows temp. This directory is used to hold temporary files for all users in the system. We would like for everyone on the system to be able to create files and folders here. You might think that we should use modify or full control for this, but we don't want users to be able to delete each other's files. Let's take a look at some of the DACLs assigned to this folder and figure out how to do this. First, local administrators and the operating system's computer account have full permissions over this folder and all files and folders within it. We see a new descriptor, IO, which indicates that this DACL is inherit only. That means that it will be inherited, but it does not apply to this container, c/windows/temp. The users group includes all user accounts on the local machine. We're going to let users WD, or create files and write data, AD, create folders and append data, and S for synchronize. You can see in the next supplemental reading that these special permissions are included in the modify simple permission. Unlike the modify simple permission, we are not granting users the ability to delete files or folders. We do want users to be able to delete their own files and folders though. So how do we do that? So if you see creator owner is a special user that represents the owner of whichever file the DACL applies to. In this directory and all subdirectories, whoever owns a file or folder has full control of it. Nice. So I'm going to create a folder and file in c/windows/temp and see what DACLs are applied. Let's use what we learned about output redirection to record the output of the iCackles in this file. So iCackles example or C Windows temp example. Then we're going to use our redirector output to give us iCackles.txt. Okay, now let's look at the file we created to view the output of iCackles. Cool, I created the files so I have full control of them, and all the other DACLs that we saw in C Windows temp have been inherited. You can see that using the special permissions in NTFS DACLs can be complicated, but it can also let you create really powerful sets of permissions customized to your exact needs. In Linux, we also have special permissions. What if I want a user to be able to do something that requires root privileges, but I don't want to give them these privileges? What's the use case for this? Glad you asked. There are certain commands that need to change files that are owned by root. Normally, if you need to change a file owned by root, you would have to use sudo. But we want to be able to have normal users change these files without giving them root access. Let's check out an example. Let's say I want to change my password. I would use the password command like we've learned. Pretty simple, right? Now I just enter in my new password, and my password is changed. We know that the password command secretly scrambles up our passwords, then adds them to this etc shadow file. Let's dive a little deeper into this file. Oh, it says this file's owned by root. How are we able to write our scrambled passwords in this file if it's owned by root? Well, thanks to a special permission bit known as setUID, we can enable files to be run by the permissions of the owner of the file. In this case, when you run the password command, it's being run as root. Let's verify this. We see the permissions on this file look a little odd. There's an S here where the X should be. The S stands for setUID. When the S is substituted where a regular bit would be, it allows us to run the file with the permissions of the owner of the file. To enable the setUID bit, you can do it symbolically or numerically. The symbolic format uses an S, while the numerical format uses a 4, which you prepend to the rest of the permissions like this. Similar to setUID, you can run a file using group permissions with setGID or setGroupID. This allows you to run a file as a member of the file group. Aha! Under our group permissions, we can see that the setGID bit was enabled, meaning that when this program is run, it's run as the group TTY. To enable the setGID bit, you can do something similar to setUID. The only difference is the numerical format uses a 2. So I can do something like this. Or something like this. There's one last special permission bit we should cover, and that's the sticky bit. This bit sticks a file or folder down. It makes it so anyone can write to a file or folder, but they can't actually delete anything. Only the owner or root can delete anything. Let's look at permissions for a /temp directory, where a lot of programs write temporary files to, and you'll see what I mean. I added the D flag to show information just for the directory and not the contents, but as you can see, there's a special permission bit at the end here, T. This means everyone can add and modify files in the /temp directory, but only root or the owner can delete the /temp directory. You can also enable the sticky bit using a numerical or symbolic format. The symbolic bit is a T and the numerical bit is a 1. So sudo chmod plus T my folder, or sudo chmod 1755 my folder works. So let's verify. Phew, that was a lot of information on special bits. You usually won't have to deal with these permission bits in a practical day-to-day manner, but it's important to know they exist in case you ever want to allow users to either share folders or even run commands with escalated privileges. User access, group access, passwords, and permissions are all core concepts in security. Right now, you're only working with permissions and access on a single computer scale. Eventually, you'll learn about access on multi-user levels across different networks and more in the next course on system administration and IT infrastructure services. For now, congratulations! You've just taken your first step toward building a foundation of computer security knowledge. In the next module, we're going to switch gears and talk about our OS and how it manages software. Next, we've got 2 assessments for you covering Windows and Bash permissions. Once you're finished, you're granted permission to take a break before we hit the ground running in the next module. Congrats! You've made it to the halfway mark in this course. You already learned how to navigate around the Windows and Linux file systems. You also learned how to manage users and groups, and the basics of permissions and access. Nice work! Next, we're going to learn about packages and the major package managers for Windows and Linux. Installing and maintaining packages is something you'll do almost every day in an IT support role, so you should be familiar with how this works on the Windows and Linux OSs. Let's get to it. Have you ever wondered how we get software like the apps in the App Store or packages on the internet to install on our devices? Wonder no more. Developers and organizations that make the software we use generally package them up nicely for us. In most cases, all we need to do is click Install, and the package gets installed for us. Packaging comes in all sorts of shapes and sizes. It's just like how you'd package a gift for someone. You could put it in a box or a bag, but the contents are what really matter. Developers have different ways to package software using software compiling tools, but the end result is a package. In the next few videos, we'll discuss some of the most common package types you'll see when you work in IT support. In Windows, software is usually packaged as a .exe or executable file. Executable files contain instructions for a computer to execute when they're run, like copy this file from here to here, install this program, or more generically, perform this operation. The concept of an executable file isn't unique to Windows, but Windows has its own special implementation of them in the form of EXEs. They're created according to Microsoft's Portable Executable, or PE format. Although we won't get into the details of the PE format, it's good to know that EXE files don't just contain instructions for the computer to perform. They also include things like text or computer code, images that the program might use, and potentially something called an MSI file. A Microsoft install package, or MSI, is used to guide a program called the Windows installer in the installation, maintenance, and removal of programs on the Windows operating system. Besides using the GUI setup wizard to guide the user in installing the program, the Windows installer also uses the MSI file to create instructions on how to remove the program if the user wants to uninstall it. Windows executable files are usually used as starting points to bootstrap the Windows installer. In this case, they might just contain an MSI file and some instructions to start up the Windows installer and read it. Alternatively, executables can be used as standalone custom installers with no MSI file or usage of the Windows installer. If they're packaged this way, the exe file will need to contain all the instructions the operating system needs to install the program. So when would you use an MSI file and the Windows installer? And when would you use an executable with a custom installer packaged in something like setup.exe? Great questions. If you want precise granular control over the actions Windows takes when installing your software, you might go the custom installer route. This can be tricky though, especially when managing things like code dependencies, which we'll talk about later. On the flip side, using the Windows installer guided by an MSI file takes care of a lot of the bookkeeping and setup for you. But it has some pretty strict rules about how the software gets installed. As of Windows 8, Microsoft has introduced a platform to distribute programs called the Windows Store. The Windows Store is an application repository or warehouse where you can download and install universal Windows platform apps. Those are the applications that can run on any compatible Windows devices like desktop PCs or tablets. These programs use a format called APPX to package their contents and act like a unit of distribution. We won't go into detail about APPX packages, but it's good to know they're out there, giving you another option for packaging software. Feel free to read more about APPX packages and how to make them in the supplemental readings I've included after this video. We learned how to install exe packages in an earlier course. To install an exe from the GUI, all we need to do is double-click on the executable, then go through the installation process provided, either by the executable itself or the Windows installer. That's pretty straightforward, but what about installing software from the command line? And why would you need to do this in the first place? Hold on to your desktops because you're about to find out. Installing executables from the command line can be handy in lots of IT support scenarios, including automatic installations. You might want to write a script or use the configuration management tool to install some software automatically without needing a human to click buttons in an installation wizard. So how can you install an executable from the command line? The answer? It depends. Pretty unsatisfying, I know. Running exe files from the command line is pretty simple. You open up a command prompt or PowerShell, change into the directory where the executable is, and type in its name. You can also just type the absolute path of the exe from wherever you are in the file system, like this: c/users/cindy /desktop hello.exe. Running from an installer from the command line is similar, but will potentially have more options for installation. Depending on the installer, you might have flags for things like a silent installation, where nothing shows up on the screen and the package is installed quietly. Or you might get an argument to have the computer reboot automatically after the package is installed. You can check out the options for packages created by using the Microsoft Self-Extractor in the supplemental reading for a better idea of what we're talking about. A given installer might have these kinds of options for installing from the command line, but they vary from vendor to vendor. The options available for a Microsoft package might differ from the options for a Mozilla package. Pro tip, try using the / parameter when running a package from the command line to see what kinds of subcommands the package might support. If the package doesn't have any help-related options, your best bet is to check out the vendor's documentation for what kinds of installations their software packages support. In Linux, there are lots of different distributions, and each might have different package types. For example, in the Linux distribution or distro Red Hat, the packages that are used are .rpm or Red Hat Package Manager packages. We won't cover how to work with RPM packages, but just be aware that package types can change when you're working with different Linux distributions. If you're interested in learning more about RPM packages, I've included a link in the supplementary reading right after this video. In this course, we'll be working with Debian packages, which Ubuntu uses. A Debian package is packaged as a .deb file for Debian. You've already learned how to install a Linux package using the help of a package manager in the first course on Technical Support Fundamentals. We'll dive deeper into this in a later video, but let's focus now on how to install a single standalone Debian package. You'll have to work with standalone Debian packages, especially when developers package and release their software on different websites. To install a Debian package, you'll need to use the dpackage or Debian package command. There's a standalone package here for the open source text editor Atom. Let's go ahead and install it using dpackage. We have to use the I flag for the install. And that's it. Now it's installed on this computer. How about if we wanted to remove a package? To do that, we use the R or remove flag. And that's how you install and remove a standalone Debian package. Pretty simple, right? You can also list the Debian packages that are installed on your machine with the dpackage-L. The L is for list. Oh, there are lots of programs on here. It looks kind of messy. Can you think of another command that we've used before that would help us search if a certain package is installed? That's right, the grep command. Let's say we want to search for the Atom package we just installed. Keep in mind I just uninstalled it, so I'm just going to install it really quickly. Alright, now let's run dpackage-L grep Atom. Here we have the dpackage-L command that's been piped to grep. Remember, the pipe command takes the standard output of one command, which in this case is the output of dpackage-L. Then it sends it to the standard input of the command it pipes to, in this case grep. If we run this command, it shows us that Atom is definitely in the list of packages here. Just remember that when using grep, it lists other results that have the search terms in the name. Just like that, we've learned how to install any Debian package in Linux. We're really cooking now. Great work! One type of package that we haven't discussed yet isn't really a package at all. It's an archive. An archive is comprised of one or more files that's compressed into a single file. Package archives are basically the core or source software files that are compressed into one file. When we install software from a source archive, it's referred to as installing from source. Popular archive types you'll see are .tar, .zip, and .rar. To install software found in an archive, you first have to extract the contents of the archive so you can see the files inside. Then, depending on what type of code it was written in, you have to use a specific method to install it. We won't discuss how to install from source, since it changes depending on what language the software was written in. But we'll discuss how to extract the contents of an archive, which you'll have to do a lot as an IT support specialist. It's not just software that's stored in an archive. Anything can be archived, like pictures or music files. You'll see these a lot in IT support. To make things more complicated, archive types have lots of different ways they can be extracted. Luckily, there's a very popular tool in Windows for file archiving and unarchiving different file types, like .rar, .zip, and tar. This is the open source tool 7-Zip. It's already installed on my computer. If you want to download it yourself, I've included a link in the supplemental reading. There's an archive on my desktop called colors.zip. Let's go ahead and extract this archive so we can see the files inside. I'm just going to right-click, 7-Zip, extract here. Looks like there are a bunch of files inside this archive. Besides unarchiving files, you can also archive files. I'm going to make a new folder called New Colors. Then I'm going to add this new blue.txt file and the old colors in this folder. Then I'm just going to archive it with 7-Zip and add to archive. Click OK. Pretty cool, right? Now, if you wanted to send someone a bunch of files in an email, you don't have to send them one by one. Instead, you can combine them all in one archive and send one single file. If you're using PowerShell version 5.0 or greater, you can actually extract and compress archives right from the command line. Let's say you've got a bunch of files in a folder called Cool Files on your desktop that you'd like to add to a new zip file. After you've opened up the PowerShell command line interface, you could issue this command: compress archive.path cool files, and then we're just going to make a new archive in the desktop called cool archive.zip. Now if we check our desktop, there you should see it, cool archive.zip. This will take everything from the desktop cool files directory and compress it into this cool archives.zip. .7-Zip is also available to use in Linux. We've already installed the package p7zip-full, which is what the Linux version of 7-Zip is. To extract a file using 7-Zip, use the command 7z and the flag E for extract, and then the file you want to extract. For example, let's extract this tar file in my home directory. And just like that, we now have the extracted contents. There are lots of other tools out there for archiving and unarchiving files. One tool that lots of people use that's already installed on most Linux distros is the tar command. We won't go over how to use this command, but if you'd like to read more about it, check out the next supplemental reading. You'll see lots of different types of archives as you work with Windows and Linux. Just keep in mind that different archive types might require different commands to extract. So you've learned what the standalone packages are for Windows and Linux, along with some of the common archive types. Well done! Next, we'll dive a little deeper into packages and some issues you might encounter when you install a standalone package. Packages of software usually rely on other pieces of code in order to work. Let's say you're installing a game on your Windows computer. The program might need to do some calculations to make the physics of the game work properly and render the results in the form of graphics on the screen. To perform these tasks, the game might have a dependency on a physics engine to do the calculations and a rendering library to show the sweet graphics on the screen. In order for the game to work, you'll have to have all that software available to the game. Counting on other pieces of software to make an application work is called having dependencies, since one bit of code depends on another in order to work. In our example, the game depends on both the physics engine and the rendering library to run. But wait, what do we mean when we refer to a library? You can think of a library as a way to package a bunch of useful code that someone else wrote. This code is bundled together into a single unit. Programs that want to use the functionality the code provides can tap into it if they need to. In Windows, these shared libraries are called Dynamic Link Libraries, or DLL for short. You can find out more details about dynamic link libraries in the next reading. One super useful feature of a DLL is that the same DLL can be used by lots of different programs. This means all that shared code doesn't need to be loaded into memory for each application that wants to use it, so less memory overall is used. Windows applications typically have many dependencies all located together in a single installation package, along with something called an MSI file that tells the Windows installer how to put it all together. This means that a given installation package will have all the resources and dependencies like DLLs right there in the package. The Windows installer will also handle managing those dependencies and make sure they're available to the program. In the old days, things weren't always so great. Imagine this scenario. A video player you've been using to play movies on your computer uses a graphics DLL to display films on your screen. A new game just came out that you want to play, so you install that too. The game comes along with a new version of that graphics library, so the game installer updates the existing version with the new DLL. All of a sudden, your video player stops working. It turns out the video player doesn't know how to use the new version of the DLL, which is a pretty big bummer. On modern Windows operating systems, though, DLL hell is a problem of the past. To fix it, most shared libraries and resources in Windows are managed by something called side-by-side assemblies, or SXS. Most of these shared libraries are stored in a folder at c/windows/win-sxs. If an application needs to use a shared library to perform a task, that library will be specified in something called a manifest. This tells Windows to load the appropriate library from the SXS folder. The SXS system also supports access to multiple versions of the same shared library automatically. So when you install software, you don't pull the rug out from underneath the programs you've already got. In addition to manifests, the SSX system and installers bundling dependencies together in their installation packages, you can use a Windows Package Manager to help install and maintain the libraries and other dependencies that your installed software needs to use. We'll talk about this in more detail in our lesson on Windows Package Managers, but we'll give you a preview using the Windows Package Management feature for PowerShell. Using a Windows Package Management commandlet called find-package, you can locate software along with its dependencies right from the command line. By the way, a commandlet is basically the name we give to Windows PowerShell commands that use the verb-noun format. We've already used lots of commandlets such as get-help, select-string, etc. There are hundreds of commandlets built into Windows, and you can even write your own. Okay, back to the task at hand. Let's say you wanted to install the sysinternals package, which is a set of tools released by Microsoft that can help you troubleshoot all sorts of problems on your Windows computers. You could download the sysinternals package from the Microsoft website, or you could use the package management feature. First, we'll need to open up a PowerShell terminal by typing in PowerShell from the Start menu. Then we can try to locate the sysinternals package by executing this command. Find-package sysinternals-include dependencies. An error. No match found. What's that all about? This exception was generated because the default source of packages in PowerShell is the PowerShell gallery, which doesn't contain the sysinternals package. Luckily, all we need to do is tell PowerShell about a place where it can find the sysinternals package. And that's a package repository called Chocolatey. We'll dip into more about Chocolatey in the Package Manager video, but for now, just know it's a place where all kinds of Windows software packages live. So before we can install any packages, we need to add a package source that tells our computer where it can find the packages we want to install. Since we want to use Chocolatey to find our packages, we need to add it as a package source. We're going to do that with the PowerShell command register-package source. So let's go ahead and type register-package source-name Chocolatey -provider name Chocolatey -location We can verify both sources of software are now good to go with the get-package source command. And then try to locate our package and its dependencies again with find-package sysinternals-include dependencies. Sweet! Now that we know that's the package we want, we can use a commandlet called install-package to actually install sysinternals and its corresponding dependencies. We'll do that in a later lesson. Now it's time for a snack break. All this chocolatey talk made me hungry. Let's see what a package dependency would look like in Linux. We learned how to install a standalone package in Linux using dpackage in the last lesson. Let's install one more package. I downloaded the Google Chrome browser here on my desktop, and I want to install it with sudo dpackage-i Google Chrome. Oh, wait a minute. What's this error I'm getting? Dependency problems prevent configuration of Google Chrome stable. This is saying it can't install Google Chrome because it's dependent on another package that isn't currently installed on this machine. So before we can install Chrome, we have to install this package libappindicator1. While a standalone package installer like dpackage may be quick to use, it doesn't install package dependencies for us. In Linux, these dependencies can be other packages, or they could be something like shared libraries. Linux shared libraries, similar to Windows DLLs, are libraries of code that other programs can use. So what do you do if you're stuck with a dependency error? You could install the dependencies one by one, sure, but in some cases you might see more than just one dependency. You might even see 10. This is especially true in Linux. It's not that fun to continually install programs just so you can get one program to work. Luckily for us, that's where package managers come in. Package managers come with the works to make package installation and removal easier, including installing package dependencies. We'll talk about package managers in the next lesson, but for now, it's enough to know that if you install a standalone package, you won't automatically install its dependencies. Now that we know a bit about installing software and dependencies from individual executables or package files, let's take a look at a different way to manage software installations using tools called package managers. You've actually already seen a package manager in action. Remember the apt or advanced package tool we talked about in an earlier video? Well, the advanced package tool is actually a package manager for the Ubuntu operating system. We'll talk about apt in a little bit, but you might be curious about what options you have for Windows package management. A package manager makes sure that the process of software installation, removal, update, and dependency management is as easy and automatic as possible. Think about the normal way you might install a new program on your Windows computer. You might search for it in a search engine, go to the program's website, download the installer, then run it. If you wanted to update the software, you might open up the program and use whatever mechanism it provides for you to install the new version. Lots of programs give you a way to perform automatic updates, and Microsoft takes care of the ones it writes through Windows Update. But you might even need to go back to the website you downloaded the software from originally to grab another installer for the new version. Finally, if you wanted to remove the software, you might use the Windows Add Remove Programs utility, or maybe run a custom uninstaller if it provides you with one. Some installation technologies like the Windows installer can take care of dependency management, but they don't do much to help you install software from a central catalog of programs or perform automatic updates. This is where a package manager like Chocolatey can come in handy. Chocolatey is a third-party package manager for Windows. This means it's not written by Microsoft. It lets you install Windows applications from the command line. Chocolatey is built on some existing Windows technologies like PowerShell and lets you install any package or software that exists in the public Chocolatey repository. I've included links to both in the next reading. You can add any software that might be missing to the public repository. You can even create your own private repository if you need to package something, like an internal company application. Configuration management tools like SCCM and Puppet even integrate with Chocolatey. That helps make managing deployments of software to the Windows computers in your company automatic and simple. We've talked about a few ways we can install packages in earlier videos. Let's add Chocolatey to the mix, which supports several methods of software installation itself. First, you can install the Chocolatey command line tool and run it directly from your PowerShell CLI. Or you can use the package management feature that was recently released for PowerShell. Just specify that the source of the package should be the Chocolatey repository. Remember this from our talk about installing software? We used this command to locate the Windows sysinternals package after adding Chocolatey as a software source. Just a refresher, the command was find package sysinternals include dependencies. That's all well and good, but how do we actually go about installing this package? Well, that's where the install-package commandlet comes into play. We can use this tool to install a piece of software and its dependencies. Let's give installing that sysinternals package we found earlier a shot. So I'm just going to go install package-name sysinternals. Yep, I'm just going to confirm. And just like that, we've got our package. We can verify it's in place with the get-package commandlet. So get-package-name sysinternals. You can also uninstall a package using the uninstall-package-name sysinternals. Okay, now let's talk about the package manager used in Ubuntu called the apt or advanced package tool. We've actually already used apt in an earlier course, so hopefully this won't look new. The apt package manager is used to extend the functionality of dpackage. It makes package installation a lot easier. It installs package dependencies for us, makes it easier for us to find packages that we can install, cleans up packages we don't need, and more. Let's see how we would install the open source graphical editor GIMP using apt. And if you want to follow along on your own machine, I've included a link to the GIMP download in the next reading. So sudo apt install GIMP. Let's take a look at what this command is doing. Apt grabs the dependencies that this package requires automatically and asks us if we want to install it. You can see this line here. 0 upgraded, 18 newly installed, 0 to remove, and 16 not upgraded. This gives us a good overview of what we're doing to the packages on our machine. Now let's remove this package with sudo apt remove GIMP. You can see that it removes dependencies for us that we're not using anymore because we don't need GIMP. You'll also notice that when installing this package, we didn't have to download the GIMP package. It was just on our system. How's that possible? Well, thanks to something known as a package repository, we don't have to manually search for each and every software we want online. We've already seen the Chocolatey package repository in action. Repositories are servers that act like a central storage location for packages. Lots of software developers and organizations host their software on the internet and give out a link to where that location is. You can add that link to your own machine so it references that package or list of packages. You've already seen this with the register-package source commandlet when we added this location of the Chocolatey repository. So in Linux, where do you add a package or repository link? The repository source file in Ubuntu is /etc/apt/sources.list. Your computer doesn't know where to check for software if you don't explicitly add the package or repository links to this file. Let's just open this up real quick and take a peek. There's some extra information in here that isn't important, but you can see here that there are links here. If you navigate to those links, you'll see a directory that holds lots of packages. Ubuntu already includes several repository sources in here to help you install the base operating system packages and other tools too. If you work in a Linux environment, there are also special repositories called PPAs, or Personal Package Archives. PPAs are hosted on Launchpad servers. Launchpad is a website owned by the organization Canonical Limited. It allows open source software developers to develop, maintain, and distribute software. You can add PPAs like you would a regular repository link, but be a little careful when using a PPA instead of the original developer's repositories. PPA software isn't as vetted as repositories you might find from reputable sources like Ubuntu. They can sometimes contain defective or even malicious software. One more thing to call out about repositories is that the repository managers update their software pretty regularly. If you want to get the latest package updates, you should update your package repositories with the apt update and then apt upgrade commands. The apt update command updates the list of packages in your repositories so you get the latest software available, but it won't install or upgrade packages for you. Instead, once you have an updated list of packages, you can use apt upgrade and it'll install any outdated packages for you automatically. Before installing new software, it's good to run apt update to make sure you're getting the most up-to-date software in your repositories. You'll also want to run apt upgrade to install any available updated packages on your machine. You can use the apt -- help command to learn more about the commands available with apt. We won't cover them all, but you can list packages, search packages, get more information about packages, and more. There are lots of different package managers you can use with Ubuntu. We chose apt because it's a popular package manager, but you can read up on an alternative package manager in Ubuntu in the next supplemental reading. Awesome! Now that you've added the apt command to your toolkit, you're ready to maintain packages in Linux. This is a skill you'll be using a whole lot in the IT support world. We'll talk about that and more in the next lesson. We've talked a lot about the practical aspects of installing software, which has been abstracted for us in the form of package managers. But as someone who might be working in IT, it's also important for you to understand what happens underneath the hood when installing or removing software. In other words, what really happens with the underlying technology when you perform this action. You might come across a situation where a package you install modifies a configuration file that it's not supposed to and then starts causing issues for you. So how does software installation work underneath the hood? Let's take a look at how an exe gets installed in Windows. When you click on an installation executable, what happens next depends on how the developer of the program has set their application up to be installed. If the exe contains code for a custom installation that doesn't use the Windows installer system, then the details of what happens under the hood will be mostly unclear. This is because most Windows software is distributed in closed source packages, meaning you can't look at the source code to see what the program is doing. In this case, though, although you can't read the instructions the developer has written, you can use certain tools to check out the actions the installer is taking. One way to do this would be to use the process monitoring program provided by the Microsoft sysinternals toolkit. This will show you any activity the installation executable is taking, like the files it writes and any process activity it performs. You can read more about the Microsoft sysinternals toolkit in the next supplemental reading. So what about an MSI file or an executable wrapping an MSI? Again, the application itself will be closed source, so you won't be able to peek at the source code to see what it does. But installation packages that use the MSI format have a set of rules and standards they need to conform to so that the Windows installer system can understand their instructions and perform the installation. There are more to MSI files than it might seem at first. In fact, they aren't simple files at all. They're actually a combination of databases that contain installation instructions in different tables, along with all of the files, objects, shortcuts, resources, and libraries the program will need, all grouped together. The Windows installer uses the information stored in the tables in the MSI database to guide how the installation should be performed. They'll know where files and application data should go, and any other things that should happen to successfully install the program. The Windows installer will keep track of all the actions it takes and create a separate set of instructions to undo them. This is how it lets users uninstall the program. If you're curious about the details of what goes into an MSI file or want to create a Windows installer package yourself, check out the orca.exe tool that Microsoft provides. It's a good way to satisfy your curiosity. Orca is part of the Windows SDK or Software Development Kit, but you don't need to be a programmer to use it. Orca can help you edit or create Windows installer packages, so feel free to explore what it can do. We've provided a link to the tool in the supplemental reading right after this video. Wow, there's a lot going on underneath the hood in a Windows installation, and it's all kicked off by a couple of clicks. So what about Linux? Glad you asked. That's up next. In Linux, software installations are a little bit more clear. We mentioned in an earlier lesson that you can install software directly from source code. This method changes depending on the software because different programming languages are compiled differently. We won't go in depth about software development, but let's say we had an archive with a simple package we want to install. This is my Flappy app package. I've already extracted it, so you can see there's a setup script. This is a script file that will run a bunch of tasks on the computer in order to set up the package. And then Flappy app code, this is the actual software code. The README is a pretty standard file contained in source archives that has information about the archive. It not so subtly asks you to read it before you do anything. The setup script is what we're concerned with, since it tells us how to install our package. A sample setup script can contain program instructions like compile Flappy app code into machine instructions, copy compiled Flappy app binary to /bin directory, or create a folder to /home/ whatever the username for a Flappy app is. This is a very simple overview of what happens when you install a simple package. In the end, the software developers decide what their software needs to work and runs tasks to get it working. It's up to the developer whether those tasks are creating files or updating directories. If you knew the programming languages used, you could read these instructions yourself, but that's a bit out of scope for this course. Anyways, that's how software installation works in Linux in a nutshell. Okay, now that you know how to view information about users and the hierarchy of user permissions, let's learn how to add and remove users on our machine. To add a user, we're going to go back to our computer management tool. Under local users and groups, we're going to right-click and select New User. From here, it asks us to set a username, a full name, and a password. Remember that in order to use good password setting practices, we set a default password and then make the user change that password when they log in. So we're going to go ahead and set a default password and make sure the box for user must change password at next logon is checked, and then click Create. So I'm just going to make a new user account for Elizabeth and have a password, and then just make sure that's checked and hit Create. And that's how you create a local user. To remove a user, we simply right-click and select Delete. This gives us a warning message that says usernames are unique, and even if you delete the user and give them the exact same username, they won't be able to access their old resources. Once you confirm that you want to do that, just go ahead and delete it. And that's how you remove a local user account. Adding and removing local user accounts from the CLI is going to use the same net command that we use to change passwords, just with different parameters. Like before, there's a native PowerShell command, new-local user, that requires a little bit of scripting to use. If you want to use new-local user, check out the supplemental reading. Now, back to net. To add a new local user, we simply use the /add parameter. If we add the /add parameter to the same command we used before, it instructs net to create the account. We can still use the asterisk for the password to be prompted to enter a password. Let's test this out and create a new account for Andrea. So net user Andrea */add. Now, let's list the user accounts to be sure it worked. So get-local user. Sweet, there it is. Now there's a small problem which you saw in the earlier lesson on passwords. This account is for Andrea, but we know what the password is. We don't want to know what the password is because that means we can log in as Andrea. We want to make sure that Andrea changes her password to something that we don't know. So we're going to flag her account as requiring a password change using the /logon password change yes parameter. So net user Andrea /logon password change yes. Now you won't know what her password is. You can actually combine these two commands that we ran to create a new account that requires a password change at first login. Let's create an account for Caesar. So net user Caesar, add a password, /add /logon password change yes. Now when we run the get-local user, we should see both of our new accounts. Sweet, and there it is. Caesar's new account has a password that you know, and you can give it to him, but he'll have to change the password the first time he logs in. Alright, now let's remove these accounts that we just created. I'm going to show you how to do this using net and using remove-local user. Both of these commands will do the exact same thing. So let's delete Andrea's account, net user Andrea /delete. This will delete Andrea's account. And using the remove-local user command, we can remove Caesar's account. Sweet, now it's gone. See how each of these options follows a pattern? The net user example looks just like it did to create a new user account, except instead of adding an account, we deleted the account. In the second example, instead of getting, setting, or creating a new -local user, we remove the account. As you continue to learn new CLI commands, you'll start to notice these sorts of patterns. Being able to identify these patterns will help you discover new things that you can do, and remember how to do things you haven't done in a while. Ubuntu has a slightly messier way of showing us device management. In Linux, everything's considered a file, even hardware devices. When a device is connected to your computer, a device file is created in the /dev directory. Let's take a look at this directory. There are lots of devices in this directory, but not all of them are actually physical devices. For example, the /dev/null device is in here. We won't talk about all the device types in Linux because there are a lot of them, but we'll go over the more common ones you'll see: character devices and block devices. Character devices, like a keyboard or mouse, transmit data character by character. Block devices, like USB drives, hard drives, and CD-ROMs, transfer blocks of data. A data block is just a unit of data storage. Remember from an earlier lesson that the first bit you see in an ls-l command is the type of file? So far, we've seen dash, which stands for a regular file, and a D, which stands for a directory. But in this output, we can see we have a few other file types. Some of them have B for block device and C for character device. If you'd like to learn more about the other device types, you can check out the next supplemental reading. Let's look at some of the block devices we'll be interacting with in this course. You'll see a few files that start with /dev/sda or /sdb. SD devices are mass storage devices like our hard drives, memory sticks, etc. If you see an A after SD, it just means the device was detected by the computer first. So you might see something like /dev/sda, /dev/sdb, /dev/sdc. Revisiting the /dev/null device, we can see it's considered a character device because it's used to transfer data character by character. This is a pretty simple overview of device files. I left a lot of stuff out that you don't necessarily need to know now. If you want to learn more about the inner workings of devices in Linux, check out, you guessed it, the next supplemental reading. Let's talk about updating device drivers for Linux. With Windows, we were able to just click Update Driver, and in most cases, that works. In Linux, things are a little more complicated, and at the same time, pretty easy. I'm not trying to be confusing, you'll see what I mean in a moment. Device drivers aren't stored in the /dev directory. Sometimes they're part of the Linux kernel. Remember that the kernel of our machine handles the interaction with hardware. The kernel is a really monolithic piece of software that has lots of functions, including support for lots of hardware. These days, a lot of hardware support is built into the kernel, so when you plug in a device, it automatically works. But if there are devices that don't have support built into the kernel, they most likely have something called a kernel module. Well, what's this kernel module thingy? For a lot of developers, touching software like the Linux kernel is kind of intimidating. Instead, they can create kernel modules which extend the kernel's functionality without them actually touching it. So if you need to install a kernel module for a specific type of device, you can install it the same way we've been installing all software in Linux. Keep in mind that not all kernel modules are drivers. We won't get into kernel modules, but if you'd like to read more, I've included a link to that as well in the next reading. Since we just need to get started and get hands-on with the operating systems, this should be more than enough. Let's keep moving. You've made it to the last lesson in this module, where we're going to cover the most important software, the operating system. We've already looked at how to install and maintain applications like a word processor, graphical editor, etc. Then we looked at how to install device driver software too. Now, we're going to look at the core operating system updates. Spoiler alert, they work just the same way as every other software we've installed. It's important to keep your operating system up to date for lots of reasons. You want the newest features that your operating system has, and you want the security updates that your operating system needs. When your operating system manufacturer discovers a security hole in the OS, they do their best to create a patch for this hole. A security patch is software that's meant to fix up a security hole. When you have an operating system update with security patches, it's vital that you install those patches right away. The longer you wait, the more prone you are to being affected by a security hole. As an IT support specialist, it's very common to routinely install operating system updates to keep your system up to date and secure. Windows usually does a great job of telling you when there are updates to install. The Windows Update client service runs in the background on your computer to download and install updates and patches for your operating system. It does this by checking in with the Windows Update servers at Microsoft every so often. You can learn more in the next reading. If it finds updates that should be applied to your computer, it'll download them, if you decided to allow it to. More on that later. Once the download has completed, depending on your Windows Update settings, the Windows Update client will ask you if it's okay to install the updates or just go ahead and install them automatically. This process usually requires a restart of your computer, which the client performs after requesting permission. In versions of Windows before Windows 10, you can tell Windows to manage your updates in a few different ways. You can have the Windows Update client install updates and patches that Microsoft releases automatically, or you can let Windows Update know that you want to decide whether or not you'd like to download and install them. You can even turn off updating entirely, but that's probably not a good idea for the security reasons we talked about. You can configure Windows Update by searching Updates in the search box and going to Windows Update setting. From there, you can tell the Windows Update client to check for new updates, look at the history of updates installed, or change the way that it'll download and apply patches by clicking into the Settings section. From there, you can tell the Update client how you want to manage your updates and even set a time when you want them installed. Windows 10 does things differently. Instead of downloading a handful of independent updates that you can choose to apply or not apply to your computer, updates are cumulative. This means that every month a package of updates and patches is released that supersedes the previous month's updates. The idea behind this is that computers will need to download less stuff in order to be up to date. As an example of how this might be beneficial, think about a Windows machine that's been turned off for a while. When it boots up again after a long period of inactivity, it'll need to download all of the updates that it's missed and apply them. If it's been off for a really long time, this could mean that it'll need to download and apply hundreds of updates. With the cumulative update model, a computer like that would only need to download the latest cumulative update, then be good to go. One downside to this is that in Windows 10, installing updates is no longer optional. You also can't pick and choose the updates you want to apply, since they're all rolled into one monthly release. Microsoft has announced that the update model in Windows 7 and 8 will also be moving in this cumulative package direction, so Windows 10 users won't be alone. In Linux, you've already learned how to update and upgrade software on your machines. When using the apt-update and apt-upgrade command, they might already install security updates for you. But when you run apt-upgrade, it doesn't upgrade the core operating system. In Windows, our OS package is Windows 10. In Linux, it's the kernel along with other packages. The kernel controls the core components of our operating system. Like our word processors, the kernel is just another package. The kernel developers regularly include security patches, new features, and fixes for bugs in their updates. If you want to get all these things, you should be running a new kernel. To first view what kernel version you have, we're going to learn a new command called uname. The uname command gives us the system information. If you use the -R flag for kernel release, you'll see what kernel version you have. You can see that I have kernel version 4.1 on here. To update the kernel and other packages, we use our nifty apt command with the option full-upgrade. Before running this command, remember to update your application sources with apt-update. So sudo apt-update. And now we can run sudo apt full upgrade. If there's a new version of the kernel available, it'll install it for us. Once you reboot the computer, you can start using it. You can verify the latest kernel is being used with the uname-r command. We left out a few details about kernel installations and security updates, but this is a good start to updating your system. If you're curious about learning the intricate details of kernel and Linux updates, check out the supplemental reading. With that, we've covered all the essentials to help you hit the ground running with software installation and maintenance. Great work! You learned how to install standalone packages, use package managers, and work with archives, device drivers, and core operating system updates. These skills will be super useful as an IT support specialist. Next, we're testing you again on both Bash and Windows. When you've finished, I'll see you in the next module. Wow, we've covered a lot of material so far. In the last lesson, we went over how to install, uninstall, and maintain software in the Windows and Linux OSs. These are tasks that you'll find yourself doing over and over as an IT support specialist. In this lesson, we're going to cover another very important function of an IT support specialist, working with disks. In our first course, Technical Support Fundamentals, we learned about physical disks like hard disk drives and SSDs. In this lesson, we're going to expand on that and talk about the tools needed to make a disk usable in a computer. Ready? Let's get started. You may remember that we introduced the concept of a file system in the Technical Support Fundamentals course. Here's a refresher. A file system is used to keep track of files and file storage on a disk. Without a file system, the operating system wouldn't know how to organize files. So when you have a brand new disk or any type of storage device like a USB drive, you need to add a file system to it. There are lots of file systems out there, but the two that we'll talk about in this course are recommended as default file systems for Windows and Linux. For Windows, we use the NTFS file system, and for Linux, it's recommended to use ext4. File systems have different compatibilities with different OSs. Most of the time, cross-operating system support is minimal at best. Let's say you have a USB drive that's using an NTFS file system. Both Windows and Linux's Ubuntu can read and write to the USB drive. But if you have an ext4 USB drive, it'll only work on Ubuntu. And not on Windows, at least without the help of third-party tools. It's pretty likely that you'll encounter this situation in an IT support role. Let's say you have some important files on that same USB drive that you want to copy over to your Windows, Linux, and Mac OSs. What would you do then? This is a pretty common situation. You'd have to reformat or wipe the USB drive and add a file system that's compatible with all three operating systems. Luckily, there are file systems like FAT32 that support reading and writing data to all three major operating systems. FAT32 has some shortcomings though. It doesn't support files larger than 4 gigabytes, and the size of the file system can't be larger than 32 gigabytes. This might be enough for a small USB drive, but it's not really great for anything else. You can learn more about FAT32 in the next supplemental reading. This still begs the question, what if you wanted to be able to share files between multiple OSs and don't want to deal with file system limitations? Don't worry, we've got you covered. In the next course on System Administration and IT Infrastructure Services, we'll discuss another file system type called Network File Systems that solves this exact problem. Alrighty, now that you've got a quick refresher on file systems, let's spend the next few lessons discussing how you actually set them up. Before we start adding a file system to a disk, let's do a rundown of the components of a disk that allow you to store and retrieve files. A storage disk can be divided into something called partitions. A partition is just a piece of the disk that you can manage. When you create multiple partitions, it gives you the illusion that you're physically dividing a disk into separate disks. To add a file system to a disk, first you need to create a partition. Usually, we just have a single partition for our OS, but it's not uncommon to have multiple partitions for different uses. Let's say you want to have 2 partitions on a disk, one for a Windows OS and one for a Linux OS. Instead of using 2 machines to use both operating systems, you can just use one machine and switch between the 2 OSs on boot up. You can also add different file systems on different partitions of the same disk. Partitions essentially act as their own separate subdisks, but they all use the same physical disk. One thing to call out is that when you format a file system on a partition, it becomes a volume. Volume and partition are sometimes mistakenly used synonymously, but we want to make sure that you understand this distinction. The other component of a disk is a partition table. A partition table tells the OS how the disk is partitioned. The table will tell you which partitions you can boot from, how much space is allocated to partition, etc. There are 2 main partition table schemes that are used: MBR, or Master Boot Record, and GPT, or GUID, partition table. These schemes decide how to structure the information on partitions. MBR is a traditional partition table, and it's mostly used in the Windows OS. MBR only lets you have volume sizes of 2 terabytes or less. It also uses something called primary partitions. You can only have 4 primary partitions on a disk. If you want to add more, you have to take a primary partition and make it into something known as an extended partition. Inside the extended partition, you can then make something called a logical partition. It's a little odd to get at first, but that's just how the partition table was created. MBR is an old standard, and it's slowly being faded out by the next partition table scheme we'll talk about, GPT. GPT is becoming the new standard for disks. You can have a volume size greater than 2 terabytes, and it only has one type of partition. You can make as many of them as you want in a disk. In an earlier lesson, we learned about a new BIOS standard called UEFI that's become the default BIOS for newer systems. To use UEFI booting, your disk has to use the GUID partition table. Now that you know what you need to do to make a partition, let's partition an actual disk. In the next few lessons, we're going to learn how to partition and format a USB drive for each respective OS. Now that we've got a little theory under our belts, how can we actually partition a disk and format a file system in Windows? Although a quick web search will turn up all kinds of third-party disk partitioning programs other people have written, Windows actually ships with a great native tool called the Disk Management Utility. Like most things in Windows, there are a few ways to get to disk management. We'll launch it by right-clicking this PC, selecting the Manage option, then clicking the Disk Management console underneath the storage grouping. We should see a display of both the disks and disk partitions, along with information about what type of file system they're formatted with. There are all kinds of good things to know here too, like the free and total capacity of disks and partitions. One super cool property of the Disk Management console is that from here, you can also make modifications to the disk and partitions on your computer. Messing with the partition where the Windows operating system is installed probably isn't the best way to demonstrate the partitioning and formatting abilities of the Disk Management console. So let's use a USB drive instead. Once the drive has been inserted and the plug-and-play service does the work of installing the driver for it, you should see it show up in the Disk Management as an additional disk. The USB drive is currently formatted using the FAT32 file system. Let's go ahead and reformat that partition using NTFS instead. To do this, we right-click on the partition and choose Format. From this window, we can choose the volume label or name we'd like to give the disk. Let's just stick with USB drive. You can also specify the file system, which will change to NTFS. That's pretty straightforward, but there are also some other options that might not be so clear. Like, what's that allocation unit size thing? Well, the allocation unit size is the block size that will be used when you format the partition in NTFS. In other words, this is the size of the chunks that the partition will be chopped into. Data that needs to be saved will spread out across those chunks. This means that if you store lots of small files, you'll waste less space with small block sizes. If you store large files, larger block sizes will mean you'll need to read less blocks to assemble the file. We'll pick the default, which is fine in most cases. You'll also see the option to perform a quick format is available. The difference between a quick format and a full format is that in a full format, Windows will do a little extra work to scan the disk, or USB drive in our case, for errors or bad sectors. This extra work will make the formatting process a little longer, so we'll just stick to quick for now. We're on a roll and we don't want anything to slow us down. The last option on the format screen is whether or not to enable file or folder compression. The decision to enable or disable compression comes with a trade-off. If you enable compression, your files and folders will take up less space on the disk, but compressed files will need to be expanded when you open them, which means the computer's processor will need to do some extra work. We aren't particularly concerned with squeezing out every last bit of disk space, so we'll leave this box unchecked. Finally, we can hit OK to proceed with the format. Windows will warn us first that formatting the volume will erase any data that might be on it. Once we let it know that it's OK, it'll start the formatting process. After a little bit of processing, we should see the label on the partition turn to healthy. Using the GUI is pretty intuitive, but there's also a command line way to accomplish the same task. This can come in handy if you need to automate disk partitioning. To do disk manipulation from the CLI, we'll dive into a tool called DiskPart. DiskPart is a terminal-based tool built for managing disks right from the command line. Let's format our thumb drive again, but using DiskPart instead of the GUI. First, we'll plug in our thumb drive. Then to launch DiskPart, all we need to do is open up a command prompt, in this case command.exe, and type DiskPart into it. This will open up another terminal window where the prompt should read DiskPart. You can list the current disks on the system by typing list disk. Next, we identify the disk we want to format. A good signal is the size of the disk, which will be much smaller for our USB drive. Then we can select it with select, disk, and then disk 1. Now we'll wipe the disk using the clean command, which will remove any and all partition or volume formatting from the disk. With the disk wiped, we now need to create a partition in it. This can be done with the create partition primary command, which will create a blank partition for our file system. Then let's select the partition with select partition 1. That's the number of our freshly created partition. And now we'll mark it as active by simply typing active. If you guessed that the next step is to format the disk with the NTFS file system, you're right. We can do this by running this command at the DiskPart prompt. Format, FS for file system, NTFS, and the label, I'm just going to call it my thumb drive. And then the formatting type, we'll want to make it quick. This command will format the thumb drive with NTFS in quick mode, which we talked about earlier. And we just gave it the name my thumb drive. Congratulations! You've just formatted a USB drive from the command line. If you want to learn more about the options and tasks you can accomplish with DiskPart, check out the DiskPart link in the supplemental reading I've included right after this video. And there you have it. That's how you format a disk with the NTFS file system in the Windows operating system using both the command line and the GUI. If you want a refresher, feel free to watch this lesson again before heading to the next one. Now that you've formatted your new file system, there's one more step left. You have to mount your file system to a drive. In IT, when we refer to mounting something like a file system or a hard disk, it means that we're making something accessible to the computer. In this case, we want to make our USB drive accessible, so we mount the file system to a drive. Windows does this for us automatically. You might have noticed this if you plug in a USB drive, it'll show up under your list of drives, and you can start using it right away. When you're done using the drive, you'll just have to safely eject, or essentially unmount the drive, by right-clicking and selecting Eject. We'll talk about why this is important in a later lesson. In Linux, there are a few different partitioning command line tools we can use. One that supports both MBR and GPT partitioning is the parted tool. Parted can be used in two modes. The first is interactive, meaning we're launched into a separate program like when we use the less command. The second is command line, meaning you just run commands while still in your shell. We're going to be using the interactive mode for most of this lesson. Before we do that, let's run a command to show what disks are connected to the computer using the command line mode. We can do this by running the parted-l command. So sudo parted-l. This lists out the disks that are connected to our computer. We can see that the disk /dev/SDA is 128 gigabytes. I've also plugged in a USB drive, and you can see that /dev/SDB is around 8 gigabytes. Let's quickly go through what this output says. Here we can see the partition table is listed as GPT. The number field corresponds to the number of partitions on the disk. We can see that there are 3 partitions. Since this disk is /dev/SDA, the first partition will correspond to /dev/SDA1, and the second will correspond to /dev/SDA2, etc. The start field is where the partition starts on the disk. For this first partition, we can see that it starts at 1049 kilobytes and ends at 538 megabytes. The field after that shows us how large the partition size is. The next field tells us what file system is on the partition. Then we have the name, and finally we can see some flags that are associated with this partition. You can see here that /dev/SDB doesn't currently have any partitions. We'll fix that in a minute. Let's select our /dev/SDB disk and start partitioning it. We want to be super careful that we select the correct disk when partitioning something so we don't accidentally partition the wrong disk. We're going to use the interactive mode of parted by running sudo parted/dev/SDB. Now we're in the parted tool. From here, we can run more commands. If we want to get out of this tool and go back to the shell, then we just use the quit command. I'm going to run print just to see this disk one more time. It says we have an unrecognized disk label. We'll need to set a disk label with the make label command. Since we want to use the GPT partition table, let's use this command. Make label GPT. Let's look at the status of our disk again. To do that, we can use a print command. Here we can see the disk information for the selected /dev/SDB disk. Now it says we have the partition table, GPT. Alright, let's start making modifications to the disk. We want to partition the /dev/SDB disk into 2 partitions. Inside the parted tool, we're going to use the make part command. The make part command needs to have the following information: what type of partition we want to make, what file system we want to format, and the start of the disk and the end of the disk, like this. The partition type is only meaningful for MBR partition tables. Remember that MBR uses primary, extended, and logical partitions. Since we are formatting this using GPT, we're just going to use primary as the partition type. The start point here is 1 megabyte, and the end point is 5 gigabytes, so our partition is essentially 5 gigabytes. Remember from an earlier course that data sizes have long been referred to in 2 different ways, using the exact data measurement and the estimated data measurement. Remember that 1 kilobyte is actually 1024 bytes, while 1 kilobyte is 1000 bytes. We haven't really had to care about this distinction before. Some operating systems sometimes measure 1 kilobyte as 1024 bytes, which is confusing, but when dealing with data storage, we want to make sure we're using the precise measurements so we don't waste precious storage space. Let's opt to use megabyte and gigabyte in our partition. Next, we're going to format the partition with the file system using makefs. So I'm just going to quit sudo makefs, type is ext4, and I want to format the partition, so sdb1. We also left the rest of the disk unpartitioned because we're going to use it for something else later. With that, we've created a partition and formatted a file system on a USB drive. Remember to always be careful when using the parted tool. It's very powerful, and if you modify the wrong disk on here, it could cause a pretty big mess. Even though we've partitioned our disk and formatted a file system on here, we're not actually able to start reading and writing files to it just yet. There's one last step to get a usable disk in Linux. We have to mount the file system to a directory so that we can access it from the shell. Spoiler alert, you'll learn how to do that in the next video. To begin interacting with the disk, we need to mount the file system to a directory. You might be thinking, why can't we just cd into /dev/sdb? That's the disk device, isn't it? It is, but if we tried to cd into /dev/sdb like this, we'd get an error saying the device is not a directory, which is true. To resolve this, we need to create a directory on our computer and then mount the file system of our USB drive to this directory. Let's pull up where our partition is with sudo parted-l. Okay, I can see the partition that we want to access is /dev/sdb1. I've created a directory already under root called myusb, so let's give this a try. So sudo mount dev sdb1 myusb. Now, if we go to myusb, we can start reading and writing to the new file system. We actually don't need to explicitly mount a file system using the mount command. Most operating systems actually do this for us automatically when we plug in a device like a USB drive. File systems have to be mounted one way or the other because we need to tell the OS how to interact with the device. We can also unmount the file system in a similar way using the umount command. Unmounting is the opposite of mounting a disk, so now let's unmount the file system. I can either use sudo umount myusb or sudo umount dev sdb1. Both will work to unmount a file system. When you shut down your computer, disks that were mounted manually are automatically unmounted. In some cases, like if we were using a USB drive, we just want to unmount the file system for the USB drive without shutting down. Always be sure to unmount a file system of a drive before physically disconnecting the drive. In the case of a USB drive, we could run into some interesting file system errors if we don't do this. We'll talk more about this in an upcoming lesson. Also, keep in mind that when we use the mount command to mount a file system to a directory, once we shut off the computer, the mount point disappears. We can permanently mount a disk, though, if we need it to automatically load up when the computer boots. To do this, we need to modify a file called etc/fstab. If we open this up now, you'll see a list of unique device IDs, their mount points, what type of file system they are, plus a little more information. If we want to automatically mount file systems when the computer boots, just add an entry similar to what's listed here. Let's go ahead and do that really quickly. The first field that we need to add for etc/fstab is the UUID, or Universally Unique ID, of our USB drive. To get the UUID of our devices, we can use this command, sudo block ID. This will show us the UUID for block device IDs, aka storage device IDs. And that's it! We've covered a lot of essential disk management tasks. So far, we've partitioned a disk, added a file system, and mounted it for use. If you're curious and want to learn more about the etc/fstab file and its options, check out the next supplemental reading. Otherwise, let's move on. One term you might have heard in relation to disks and partitions is swap space. Before we talk about swap space, let's talk about the concept of virtual memory. Virtual memory is how our OS provides the physical memory available in our computer, like RAM, to the applications that run on the computer. It does this by creating a mapping of virtual to physical addresses. This makes life easier for the program, which needs to access memory, since it doesn't have to worry about what portions of memory other programs might be using. It also doesn't have to keep track of where the data it's using is located in RAM. Virtual memory also gives us the ability for our computer to use more memory than we physically have installed. To do this, it dedicates an area of the hard drive to use as storage space for blocks of data called pages. When a particular page of data isn't being used by an application, it gets evicted, which means it gets copied out of memory onto the hard drive. This is because accessing data on RAM is fast, much faster than the hard drive, where space is at a premium. Because of this, the operating system wants to keep the most commonly accessed data pages in RAM. It then puts stuff that hasn't been used in a while on the disk. This way, if a program needs a page that's not accessed a lot, the operating system can still get to it. But it has to read it from the comparatively slow hard drive and put it back into memory. Almost all operating systems use some kind of virtual memory management scheme and paging mechanism. So how does it work on Windows? The Windows OS uses a program called the Memory Manager to handle virtual memory. Its job is to take care of that mapping of virtual to physical memory for our programs and to manage paging. In Windows, pages saved to disk are stored in a special hidden file on the root partition of a volume called pagefile.sys. Windows automatically creates page files, and it uses the Memory Manager to copy pages of memory to be read as needed. The operating system does a pretty good job of managing the page file automatically. Even so, Windows provides a way to modify the size, number, and location of paging files through a control panel applet called System Properties. You can get to the System Properties applet by opening up the control panel. Going to the System and Security setting, then clicking on System. Once in the System pane, you can open up the Advanced System Settings on the left-hand menu. Pick the Advanced tab, then click on the Settings button in the Performance section. One last time, click on the Advanced tab, and you should see a section called Virtual Memory, which displays the paging file size. If you click the Change button, you can override the defaults Windows provides. So you can set the size of the paging file and add paging files to other drives on the computer. Microsoft has some guidelines for setting the paging file size that you can follow. For example, on 64-bit Windows 7, the minimum paging file size should be set to 1x, the amount of RAM in the machine. Unless you have a specific reason to change it, it's generally fine to let Windows automatically manage the paging file size itself. In Linux, the dedicated area of the hard drive used for virtual memory is known as swap space. We can create swap space by using the new disk partitioning tools that we learned. A good guideline to use to determine how much swap space you need is to follow the recommended partitioning scheme in the next supplemental reading. In our case, since we just have a USB drive which doesn't need swap, we're just going to partition the rest of it as swap to show you how this works. In practice, you would create swap partitions for your main storage devices like hard drives and SSDs. Okay, let's make swap space. First, go back into the parted tool and select /dev/SDB, where our USB is. We're going to partition it again, this time to make a swap partition, and then we'll format the Linux-swap file system on it. So make part, primary, Linux swap, 5 GB, 100%. You'll notice that the endpoint of the drive says 100%, which indicates that we should use the rest of the free space on our drive. We're not done yet. Swap isn't actually a file system, so this command won't be enough. I know, I'm sorry, I just lied to you like 5 seconds ago. If you think about it, it makes a lot of sense, since pages go into swap and not file data. Anyways, to complete this process, we need to specify that we want to make it swap space with the make swap command. Let's quit out of parted and run this command on our new swap partition. So sudo make swap dev, and our new swap partition is on dev sdb2. Finally, there's one more command to run to enable swap on the device, swap on. So sudo swap on dev sdb2. If we want to automatically mount swap space every time the computer boots up, just add a swap entry to the /etc fstab file like we did earlier. Now that we've gotten a few practical things out of the way with disk partitioning and file system creation, we can talk about concepts for a bit. Remember when we talked about how our OS handles files? It actually manages the actual file data, file metadata, and file systems. We've already covered file systems. In this video, we're going to cover the file data and file metadata. When we talk about data, we're referring to the actual contents of the file, like a text document that we save to our hard drives. The file metadata includes everything else, like the owner of the file, permissions, size of the file, its location on the hard drive, and so on. Remember that the NTFS file system is the native file system format of Windows. So how exactly does NTFS store and represent the files we're working with on our operating system? NTF uses something called the Master File Table, or MFT, to keep everything straight. Every file on a volume has at least one entry in the MFT, including the MFT itself. Usually, there's a one-to-one correspondence between files and MFT records. But if a file has a whole lot of attributes, there might be more than one record to represent it. In this context, attributes are things like the name of a file, its creation timestamp, whether or not a file is read-only, whether or not a file is compressed, the location of the data that the file contains, and many other pieces of information. When you create files on an NTFS file system, entries get added to the MFT. When files get deleted, their entries in the MFT are marked as free so they can get reused. One important part of a file's entry in the MFT is an identifier called the file record number. This is the index of the file's entry in the MFT. A special type of file we should mention in Windows is called a shortcut. A shortcut is just another file and another entry in the MFT. But it has a reference to some destination so that when you open it up, you can get taken to that destination. You can create a shortcut by right-clicking on the target file and selecting the Create Shortcut option. And there it is. Besides creating shortcuts as ways to access other files, NTFS provides two other ways using hard and symbolic links. This might get a little weird, but stay with me. Symbolic links are kind of like shortcuts, but at the file system level. When you create a symbolic link, you create an entry in the MFT that points to the name of another entry or another file. This might seem like just another way to make a shortcut, but symbolic links have a key difference. The operating system treats them like substitutes for the file they link to in almost every meaningful way. This is the part that sounds strange, so let's demonstrate. Let's create a directory on the desktop called links. Inside of it, we'll create a text file called file1. And inside of that, let's add the word hello. And then, let's make a shortcut that points to this file called file1 shortcut. Next, let's open up a command prompt and navigate to this directory. Let's try to open up file1 through its shortcut with Notepad. What do you think will happen? If you expected Notepad to display hello, then you'd be disappointed. Instead, Notepad's opened up the shortcut file, which has some text in there that isn't readable by us. Instead of a shortcut, let's create a symbolic link. You can create symbolic links with the Make Link program from the command prompt. Let's make one called file1 symlink with the following command, and then open it up in Notepad and see what happens. All right, let's open it up in Notepad. Aha! This is what we mean when we say the operating system treats a symbolic link just like the original file. There's another type of link worth mentioning called a hard link. When you create a hard link in NTFS, an entry is added to the MFT that points to the linked file record number, not the name of the file. This means the file name of the target can change and the hard link will still point to it. You can create hard links in a way that's similar to symbolic links, but with the /h option. So make link /h file1 hard link file1. Since a hard link points at the file record number and not the file name, you can change the name of the original file and the link will still work. Next, we'll have a look at how Linux organizes files and the way it treats hard links and symbolic links. Onward and upward. In Linux, metadata and files are organized into a structure called an inode. Inodes are similar to the Windows NTFS MFT records. We store inodes in an inode table, and they help us manage the files on our file system. The inode itself doesn't actually store file data or the file name, but it does store everything else about a file. In the last lesson, we learned how to create file shortcuts, symbolic links, and hard links in Windows. When Linux, we have the same concept. Shortcuts in Linux are referred to as soft links or symlinks. They work in a similar way symbolic links work in Windows in that they just point to another file. Soft links allow us to link to another file using a file name. They're great for creating shortcuts to other files. The other type of link found in Linux are hard links. Similar to Windows, hard links don't point to a file. In Linux, they link to an inode which is stored in an inode table on the file system. Essentially, when you're creating a hard link, you're pointing to a physical location on disk, or more specifically on the file system. But if you deleted a file of a hard link, all other hard links would still work. Let's actually see where hard links are referenced. If we did an ls-l on this file, important file, you'll notice the third field in the details. This field actually indicates the amount of hard links a file has. When the hard link count of a file reaches 0, then the file is completely removed from the computer. To create a soft link, we can run the command ln with the flag -s for soft link. So ln-s, important file soft link. To create a hard link, we can run the ln command without the -s to specify a hard link. So ln important file hard link. Now, if we check ls-l important file, we'll see that the hard link count was increased by 1. Hard links are great if you need to have the same file stored in different places, but you don't want to take up any additional space on the volume. This is because all the hard links point to the same space on the volume. You could use soft links to do the same thing, but what if you moved one file, broke the soft link, and forgot about all the other places that you used it? Those would be broken too and may take some time to clean up. You may not see a use for making your own soft links or hard links right now, but they're used all throughout your system, so you should be aware how they work. Now that we've taken a good hard look at files in different file systems, let's turn our attention to how we can monitor the number and size of those files in Windows. You've seen how there are loads of third-party programs out there to partition and format disks on Windows. Well, there are also lots of applications you can download that can check and visualize disk usage on a Windows machine. But you can use the disk management console we examined in an earlier lesson to get a sense of your disk capacity and usage. To check disk usage, you can open up the Computer Management utility. Then head to the Disk Management console. From there, you right-click on the partition you're interested in and select Properties. This will bring up the General tab, where you can see the used and free space on the drive. In addition to using this graphical user interface to check the disk usage, Windows provides a command line utility called disk usage as part of its sysinternals tool offering. The DU utility can print out the usage of a given disk and tell you how many files it has. It can be useful for creating scripts which might need text-based output instead of visual reports like the pie chart in disk management. You can find a link to the DU tool in the next supplemental reading. On this same tab in the Disk Management console, you might notice a button that says Disk Cleanup. If you press this button, Windows will launch a program called cleanmanager.exe, which will do a little housekeeping on your hard drive to try and free up some space. This housekeeping includes things like deleting temporary files, compressing old and rarely used files, cleaning up logs, and emptying the recycle bin. Another task related to disk health is called defragmentation. The idea behind disk defragmentation is to take all the files stored on a given disk and reorganize them into neighboring locations. Having files ordered like this will make life easier for rotating hard drive disks that use an actuator arm to write to and read from a spinning disk. The head of the actuator arm will actually travel less to read the data it needs. I should call out that this is less of a benefit for solid-state drives since there's no physical read-write head that needs to move around a spinning disk. For these kinds of drives, the operating system can use a process called trim to reclaim unused portions of the solid-state disk. We won't get into details of how trim works, but it's good to know that it exists. I've included a link to more information on trim in the reading right after this video. Defragmentation in Windows is handled as a scheduled task. Every so often, the operating system will defragment the drive automatically, and you don't need to worry about it. But you can manually defragment a drive in Windows if you want to. To kick off a manual defragmentation, open up the Disk Defragmenter tool bundled with the OS. So type Disk Defragmenter. When it launches, you'll be given a list of disks which can be defragmented, along with buttons to analyze the potential gains from running a defrag, or defragmentation, and to run the defrag itself. In the last lesson, we saw how to view the disk utilization on your computer in Windows. In Linux, we can do this using the du-h command. The du or disk usage command shows us the disk usage of a specific directory. If you don't specify a directory, it'll default to your current one. The -h flag gives you the data measurements in human-readable form. You should use the du command if you want to know how much disk space is being used by files in a directory. Another command you can use if you want to know how much free space you have on your machine is the df command, or disk free. This shows you the free space available on your entire machine. The -h flag gives you the data measurements in human-readable form. You should use the df command if you want to know how much free space you have on your entire system. You might have noticed that we didn't really touch on file system defragmentation for Linux. Linux generally does a good job of avoiding fragmentation more than Windows. We won't get into this in depth, but you can learn more in the next supplemental reading. In common IT scenarios, you might find yourself running low on disk space. It's up to you to investigate what files and folders are taking up space, and if you need to remove these files. As always, make sure to be super careful when removing files. In an earlier lesson, we talked about the dangers of unplugging a USB device without ejecting or unmounting it from the computer. You might have seen error messages like this yourself when the system alerts that you must safely eject this flash drive. Why do we need to do this? When we copy over files to a flash drive and we see that the file copied successfully, why can't we just unplug the drive without unmounting or hitting the eject button in the OS? Turns out, it may not be finished copying over that data. It's not just yelling at us for fun. When we read or write something to a drive, we actually put it into a buffer or cache first. A data buffer is a region of RAM that's used to temporarily store data while it's being moved around. So when you copy something from your OS to your USB drive, it first gets copied to a data buffer because RAM operates faster than hard drives. So if you don't properly unmount a file system and give your buffer enough time to finish moving data, you run the risk of data corruption. Data corruption can happen for lots of reasons other than unsafely removing a disk drive. Let's say you're working on your computer and the power to the building went out, causing your computer to suddenly shut off. This kind of crash also causes data corruption. System failures or software bugs can cause data corruption as well. The NTFS file system has some advanced features built into it that can help minimize the danger of corruption, as well as try to recover when the file system does get damaged. One of these features, through a process called journaling, logs changes made to a file metadata into a log file called the NTFS log. By logging these changes, NTFS creates a history of the actions it's taken. This means it can look at the log to see what the current state of the file system should be. If a crash or bug does cause corruption, the file system can initiate a recovery process that will use that log to make sure the system is in a consistent state. In addition to journaling, NTFS in Windows implements something called self-healing. As you might guess from the name, the self-healing mechanism makes changes to minor problems and corruptions on the disk automatically in the background. It does this while Windows is running, so you don't need to perform a reboot. If you want to check the status of the self-healing process on your computer, you can open up an administrative command prompt and use the fsutil tool like this. fsutil repair query, and I want to query my C drive. Finally, when things get really bad and there's some serious or catastrophic disk corruption like bad disk sectors, disk failures, and more, you can turn to the NTFS check disk utility. The recovery features NTFS has built into it mean that you don't usually need to run check disk, but is available in emergencies. To run check disk manually, you can open up an administrator command prompt and type check disk onto the command line. By default, check disk will run in read-only mode, so it'll give you a report on the health of the disk, but won't make any modifications or repairs to it. You can tell check disk to fix any problems it finds with the /f flag. You can also specify the drive you want to check, like this. Check disk /f. I'm going to check my thumb drive, which is on the D. A lot of times, you won't need to run check disk manually though. If the operating system detects that some data has been corrupted, or that the disk has a bad sector, it'll set a bit in a metadata file on the volume that indicates there's corruption. When the system boots, the check disk utility will check this bit. If it's set, it'll execute and try to repair the corruption by reconstructing the broken bits of the file system from the NTFS log. As you can see, the Windows NTFS file system has some pretty robust measures and features in place to recover and prevent corruption from breaking your partitions. Next, let's have a look at how you can perform file system repairs in Linux. To try and repair a file system manually in Linux, you can also use the fscheck or file system check command. Just make sure the file system isn't mounted. I won't run this command, but this is what it would look like. If you run fscheck on a mounted partition, there's a high chance that it'll damage the file system. File system repair isn't always a guaranteed fix, but it can help in most cases. Just be nice to your hardware, and it'll be nice to you. In most cases. Another thing to call out is that on some versions of Linux, fscheck actually runs on your computer when you boot it to check for any issues and attempt to auto-repair the file system. You can learn more about how to enable this and about some advanced features that you can use with fscheck in the next supplementary reading. We've covered a lot of essential disk management and file system concepts in this lesson. You learned how to partition a disk, how to format a file system, and how to mount a file system. We even talked about how you could repair a corrupt file system. In an IT support role, knowing how to work with disks is essential. Your customers store their precious data on these disks, and they don't want to lose those photos of their children, important presentations, their collection of music, or whatever it may be. Knowing how to work with disks and the data on them is a vital part of an IT role. Next, you guessed it, it's time for another pair of Windows and Bash assessments. Take your time with them and feel free to go back and review any material from this module beforehand if you need to.
When I was really young, my dad took me to a library at Columbia University where they had installed these terminals to connect to Columbia's mainframe. And I saw this stuff for the first time and something clicked and a light bulb went off over my head and I thought, this is how I want to spend the rest of my life. You know, I think it was kind of this concept that you could get this machine to do whatever you wanted if you just knew how to phrase it, right? And this idea that you had such control and that these were such amazing devices that the computer was like this anything box you could shape to solve any kind of problem you could imagine if you just knew how to do it. And it was incredibly addictive even before I was actually able to lay my hands on a computer. It was just addictive to know that that power was out there, and it was almost an obsession for me to try to get access and figure out how I was going to be able to use these things and work with them and learn about them. You know, my parents are both historians, and I think they thought I was some kind of freak child that had been dropped in their family by accident, and so they bought the computer for me, thinking for sure in 6 months they'd be selling it used, right? And lucky for me, they were very, very wrong.
Welcome back. 4 modules down, 2 to go in this course. Great work so far. In the last lesson, we learned how to partition and set up disks with file systems to start storing files. We also dove deeper into the details of file systems and even learned tools for repairing corrupt file systems and disks. In this lesson, we're going to talk about processes. Processes play an important part in our computer user experience. After all, why use a computer if you can't use any programs? With more and more processes running on our computer, we have to think about ways to better utilize our hardware resources. Get ready, because we're going to get into the nitty-gritty of processes. We'll talk about how to read process output and learn how to track our resources. Ready? Set? Let's go! In an earlier lesson, we learned that programs are the applications that we can run, like the Chrome web browser. Processes are programs that are running. We can have lots of processes running for the same program, like how we can have many Chrome windows open at once or lots of movies playing using one program. When we launch a process, we're executing a program, and remember, a program is just software. To calculate the information that our software contains, we need to give it resources so that it can be run. When processes are run, they take up hardware resources like CPU and RAM. Luckily, today's computers are powerful enough to handle the processes that we use in our day-to-day activities, like browsing the web, watching movies, etc. But sometimes this isn't enough. Sometimes a process is taking more resources than it's supposed to. Sometimes processes are unresponsive and freeze up our system, making our entire computer unresponsive. Well, we're going to talk about why this happens and how we can fix it in the upcoming lessons. But before we can talk about managing processes, we have to understand how they work. When you open up an application like a word processor, you're launching a process. That process is given something called a process ID to uniquely identify it from other processes. Our computer sees that the process needs hardware resources to run, so our kernel makes decisions to figure out what resources to give it. Then, in the blink of an eye, our computer starts up a word processor, and ta-da, we're ready to start working. This happens for every process you launch yourself and for every process you don't even know is running. Besides the visible processes that we start, like our music player or word processor, there are also not-so-visible processes running. These are known as background processes, sometimes referred to as daemon processes. Background processes are processes that run in the background. We don't really see them, and we don't interact with them, but our system needs them to function. They include processes like scheduling resources, logging, managing networks, and more. When we take a look at all the processes running on our system, you'll see what I'm talking about. In the next couple of lessons, we'll talk about how processes get created and terminated. Then, we can start digging into the details of process management. Process management is a vital skill in IT support. You'll often find yourself troubleshooting issues with frozen applications, slow applications, and more. The way that processes are created and stopped differs based on the operating system you use. First, let's have a look at how Windows does things. When Windows boots up or starts, the first non-kernel user mode that starts is the Session Manager Subsystem, or SMSS.exe. The SMSS.exe process is in charge of setting some stuff up for the OS to work. It then kicks off the login process, called winlogon.exe, appropriately enough, along with the client-server runtime subsystem called csrss.exe, which handles running the Windows GUI and command line console. We'll talk about a process called init in the next lesson, which Linux uses as the first process. You might be tempted to think of smss.exe as the Windows equivalent of init. Don't fall into that trap, though. When it comes to process creation mechanisms, they're all pretty different. In Windows, each new process that's created needs a parent to tell the operating system that a new process needs to be made. The child process inherits some things from its parent, like variables and settings, which we can collectively refer to as an environment. This gives the child process a pretty good start in life, but after the initial creation step, the child is pretty much on its own. Unlike in Linux, Windows processes can operate independently of their parents. Let's take a look at how this works by creating our own. First, let's launch the PowerShell process to give us a Windows command prompt. From there, we can type in notepad.exe to create a new process for the Notepad program. So far, so good. The parent process is PowerShell, and the child is the Notepad application. What happens if we kill the parent process, though, by clicking on the X button? Notice that Notepad keeps on running happily, even though its parent has been terminated. Those children are just in their own world. Clicking the X is just one way to stop a process from running in Windows. But as you might expect, there are other ways you can stop processes. You can use a command prompt command by calling on the task kill utility. Task kill can find and halt a process in a few ways. One of the more common ways is to use an identification number known as the process ID, or PID, to tell task kill which process you'd like stopped. One way to do this is to kill Notepad again by specifying the PID using taskkill/PID and then the PID number. So taskkill/PID. This is the process ID of Notepad. And success! This will send the termination signal to the process identified by the PID, which happens to be Notepad in our case. This is useful, but how do we get that PID in the first place? Glad you asked. We'll talk about how to locate and view processes and other more detailed process information in an upcoming lesson. In Linux, processes have a parent-child relationship. This means that every process that you launch comes from another process. Let's check out this command. The less command would be the parent process to our grep process. If all processes come from another process, there must be an initial process that started this all, right? Yes, there is. When you start up your computer, the kernel creates a process called init, which has a PID of 1. Init starts up other processes that we need to get our computer up and running. There are more nuances to process creation than this, but I wanted to introduce the parent process concept since you'll see them when we start managing processes. What about what happens when we're done with our processes? When your processes complete their task, they'll generally terminate automatically. Once a process terminates, it'll release all the resources it was using back to the kernel so that they can be used for another process. You can also manually terminate a process, which we'll discuss how to do in an upcoming lesson.
My name is Jessica Theodat, and I'm a systems engineer in the Site Reliability Organization. So I've been talking to one of my mentors, and I said, man, I'd really kill to have a job this summer. I would love to work with computers. And she said, well, I have this opportunity, but we're not sure if you're quite ready for it because you're a little young and inexperienced. And I pretty much backed her. She took a chance on me, and I stuck with her from the time that I was 15 until I entered college. The first time I was challenged to problem solve was probably when we got our first computer and I broke it. I was sitting at the computer, and I had been inspired by a movie that I saw and decided that I wanted to be a young hacker. And so I ran some command lines, and I managed to blue screen death the computer. And so I panicked, trying to figure out what I could do to revert what I just did, and there was no saving it. I am first generation, born in the US. My family is from Haiti. All of my life, my parents and everyone around me always asked me, what did you want to be when you grew up? I really honestly didn't know what I wanted to be until I started playing around with computers, and I eventually figured out that I had a love for it, and I basically thought to myself, there has to be a job that I can do with computers. When I said that I wanted to pursue a profession in technology and computing, no one understood what I was talking about. Coming from an immigrant family, everyone talks about being a doctor or a lawyer or a teacher, and if you're not one of the three, you're not doing it right. But now, they don't think that anymore. So they think I'm a god.
It might feel like we're starting to get into the weeds here, so let's take a step back and think about what processes really are and what they represent in the context of an operating system. You can think of processes as programs in motion. Consider all the code for your internet browser. It sits there on your hard drive, quietly waiting for its time to shine. Once you start it up, the operating system takes that resting code, then turns it into a running, responding, working application. In other words, it becomes a process. You interact with, launch, and halt processes all the time on computers, although the OS usually takes care of all that behind the scenes. By learning about processes, you're taking a peek behind the curtain at how operating systems really work. This knowledge is both fascinating and powerful, especially when applied by a savvy IT support specialist to solve problems. Keep all that in mind as we take a look at how you can pull back the curtain even further. Next, we'll learn about the different ways you can investigate which processes are running on a Windows computer and more methods of interacting with them. On the Windows operating system, the Task Manager or taskmgr.exe is one method of obtaining process information. You can open it with the Control-Shift-Escape key combination or by locating it using the Start menu. If you click on the Processes tab, you should see a list of the processes that the current user is running, along with a few of the system-level processes that the user can see. Information about each process is broken out into columns in the Task Manager. The Task Manager tells you what application or image the process is running, along with the user who launched it and the CPU or memory resources it's using. To kill a process, you can select any of the process rows and click the End Task button in the lower right corner. We can demonstrate this by launching another notepad.exe process from the command line, then switching over to the Task Manager, selecting the notepad.exe process, and ending it. I already have Notepad open, so I'm just going to click on it, click End Task. In an earlier lesson, we talked about starting and ending Windows processes. Remember that we used the task kill command to stop a process by its identification number, or PID. So how do we get that PID number? Well, in Task Manager, you can click on the Details menu option. In here, you can see a whole bunch of other information you can get the Task Manager to display, including the PID. You can also see this information from both the command prompt and PowerShell. From the command prompt, you can use a utility called task list to show all the running processes. From a PowerShell prompt, you can use a commandlet called get-process to do the same. There are lots of ways you can get process information from the Windows operating system. We've included links to the documentation of both task lists and get-process in the supplementary reading in case you want to dive deeper into either of these tools. Okay, now let's talk about how to view the processes running on our system in Linux. We'll be using the ps command, so let's just go ahead and run that command with the -x flag and see what happens. This shows you a snapshot of the current processes you have running on your system. The ps output can be overwhelming to look at at first, but don't worry, we'll walk through how to read this output. Let's start from right to left here. PID or PID is the process ID. Remember, processes get a unique ID when they're launched. TTY, this is the terminal associated with the process. We won't talk about this field, but you can read more about it in the man pages linked right after this video. Stat, this is the process status. If you see an R here, it means the process is running or it's waiting to run. Another common status you'll see is T for stopped, meaning a process that's been suspended. Another one you might see is an S for interruptible sleep, meaning the task is waiting for an event to complete before it resumes. You can read more about the other types of process statuses in the man pages. Time. This is the total CPU time that the process has taken up. And lastly, command. This is the name of the command we're running. Okay, now we're going to enter hard mode here. Run this command, ps-ef. The E flag is used to get all processes, even the ones run by other users. The -f flag is for full, which shows you full details about a process. Look at that! We have more processes and even more process details. Let's break this down. UID is the user ID of the person who launched the process. PID is the process ID. And PPID is the parent ID that we discussed in an earlier lesson, which launched the process. C is the number of children processes that this process has. S time is the start time of the process. TTY is the terminal associated with the process. Time is the total CPU time that the process has taken up. And CMD or command is the name of the command that we're running. What if we wanted to search through this output? It's super messy right now. Can you think of a way we can see if a process is running? That's right, with the grep command. I told you we were going to use it all the time. This will give us a list of processes that have the name Chrome in them. There's another way to view process information. Remember, everything in Linux is a file, even processes. To view the files that correspond to processes, we can look into the /proc directory. There are a lot of directories here for every process that's running. If you looked inside one of the subdirectories, it'll give you even more information about the process. Let's look at a sample process status file for PID 1805. This tells us even more information about a process state than what we saw in PS. While the /proc directory is interesting to look at, it's not very practical when we need to troubleshoot issues with processes. For now, stick with the ps-ef command to look at process information. As you can see, we can learn a lot about the processes running on our machine with just a few keystrokes. In an upcoming lesson, we'll talk about how to use process information to our benefit when figuring out which processes are taking up too many resources. For now, feel free to learn a little more about the processes that you're running. I'll be waiting for you in the next video. In Linux, there are lots of signals that we can send to processes. These signals are labeled with names starting with sig. Remember the sigint signal we talked about before? You can use sigint to interrupt a process, and the default action of this signal is to terminate the process that it's interrupting. This is true for Linux too. You can send a sigint signal through the keyboard combination Control-C. Let's see this in action. I'm going to do the same thing as we did in Windows and start a program like sudo parted. We can see that we're in the parted tool now. Let's interrupt this tool and say we want it to abort the process with the Control-C keyboard combination. Now we can see that the process closed and we're back in our shell. We were able to interrupt our process midway and terminate it. Success! There are lots of signals used in Linux, and we'll talk about the most common ones in the upcoming lessons. In earlier lessons, we talked about processes. We saw some examples of how to manipulate them with signals. Let's expand on that idea of process management by looking at some other things you can do to manipulate processes. In Windows, we've looked at programs like Task Manager, the PowerShell commandlet get-process, and the task list utility, to name a few. We've also seen how to send a running process a signal through Control-C. But there's another process management tool we haven't talked about, which lets you do things like restart or even pause processes. This tool is called Process Explorer. Process Explorer is a utility Microsoft created to let IT support specialists, systems administrators, and other users look at running processes. Although it doesn't come built into the Windows operating system, you can download it from the Microsoft website, which I've linked to in the supplemental reading right after this video. Once you've downloaded Process Explorer and started it up, you'll be presented with a view of the currently active processes in the top window pane. You'll also see a list of the files a selected process is using in the bottom window pane. This can be super handy if you need to figure out which processes use a certain file, or if you want to get insight into exactly what a process is doing and how it works. You can search for a process easily in Process Explorer by either pressing Ctrl-F or clicking on the little binocular button. Let's go ahead and do a search for the Notepad process we opened up earlier. You should see C/Windows/System32/Notepad.exe listed as one of the search results. If you see something that says notepad.exe.mui, don't worry. MUI stands for Multilingual User Interface, and it contains a package of features to support different languages. Anyways, once you've located the notepad.exe process, notice how it's nested under the command.exe process in the UI. This indicates that it's a child process of command.exe. If you right-click on the notepad.exe process, you'll be given a list of different options that you can use to manage the process. Check out the ones that say kill process tree, restart, and suspend. Kill process does what you might expect. Say goodbye to Notepad. Kill process tree does a little bit more. It'll kill the process and all of its descendants, so any child process started from it will be stopped. Kill process tree takes no prisoners. Restart is another interesting option. You might be able to guess what it does just by its name. It'll stop, then start the process again. Let's do that with the notepad.exe process we started from command.exe. Interesting. After the restart, notepad.exe doesn't appear as a child of command.exe anymore. What gives? Well, if we search for notepad.exe again, we can see it's been restarted as a child of the procexp.exe process. This is the process name for Process Explorer. This makes sense since Process Explorer was the process in charge of starting it again after we terminated it. But what about the suspend option? Instead of killing a process, you can use this option to suspend it and potentially continue it at a later time. If we right-click Suspend the process, we'll see that in the CPU column of Process Explorer output, the word suspended appears. While a process is suspended, it doesn't consume the resources it did when it was active. We can kick it off again by right-clicking and selecting the Resume option. Process Explorer can do a lot, and we'll take a look at some of the monitoring information it can give us in an upcoming lesson. We won't get into the details of all its features though, so if you're curious, you can check out the documentation on Microsoft's website. We put a link to it for you in the supplementary reading. Let's talk about how to use signals to manage processes in Linux. First up, terminating processes. We can terminate a process using the kill command. It might sound a bit morbid, but that's just how it is in the dog-eat-dog world of terminating processes. The kill command without any flags sends a termination signal or sig term. This will kill the process, but it'll give it some time to clean up the resources it was using. If you don't give the process a chance to clean up some of the files it was working with, it could cause file corruption. I'm going to keep a process window open so you can see how our processes get affected as we run these commands. So to terminate a process, we'll use the kill command along with the PID of the process we want to terminate. Let's just go ahead and kill this Firefox process. And if we check the process window, we can see that the process is no longer running. The other signal that you might see pop up every now and then is the sig kill signal. This will kill your process with a lot of metaphorical fire. Using a sig term is like telling your process, "Hey there process, I don't really need you to complete right now, so could you just stop what you're doing?" And using sig kill is basically telling your process, "Okay, it's time to die." The signal does its very best to make sure your process absolutely gets terminated and will kill it without giving it time to clean up. To send a sig kill signal, you can add a flag to the kill command, -kill for sig kill. So let's open up Firefox one more time. So kill, -kill, 10392. And now you can see that Firefox has been killed. These are the two most common ways to terminate a process, but it's important to call out that using kill-kill is a last resort to terminating a process. Since it doesn't do any cleanup, you could end up doing more harm to your files than good. Let's say you had a process running that you didn't want to terminate, but maybe you just want to put it on pause. You can do this by sending the sig tstop signal for terminal stop, which will put your process in a suspended state. To send this, you can use the kill command with the flag -tstop. I'm going to run ps-x so you can see the status of the processes. We're just going to put this process in a suspended state. So kill -tstop 754. Now you can see the process 10754 is now in a suspended state. You can also send the sig tstop signal using the keyboard combination Ctrl-Z. To resume the execution of the process, you can use the SIG CONT for continue signal. Let's go ahead and look at the process table again. I'm going to go ahead and use that command on this process. Now if I look at the process again, you'll see that the process status turned from a T to an S. SIG term, SIG kill, and SIG T-stop are some of the most common signals you'll see when you're working with processes in Linux. Now that you have a grasp on these signals, let's use them to help us utilize hardware resources better. You've been doing a great job, and we're almost done with this module. Okay, now that we've spent all this time learning about processes, like how to read them and how to manage them, when are we ever going to use these newfound skills? Well, pretty much all the time. But in an IT support role, managing processes comes in handy the most when processes become a little unruly. Our systems usually have some pretty good ways of monitoring processes and telling us which processes might be having issues. In Windows, one of the most common ways to quickly take a peek at how the system resources are doing is by using the Resource Monitoring tool. You can find it in a couple places, but we'll launch it right from the Start menu. Once it opens, you'll see 5 tabs of information. One is an overview of all the resources on the system. Each other tab is dedicated to displaying information about a particular resource on the system. You'll also notice that Resource Monitor displays process information too, along with data about the resources that the process is consuming. You can get this performance information in a slightly less detailed presentation from Process Explorer. Just select the process you're interested in, right-click, and choose Properties. From there, pick the Performance Graph tab. You can see quick visualizations of the current CPU, memory, indicated by private bytes, and disk activity, indicated by I/O. But how can we get this information from the command line? I'm glad you asked. There are several ways to get this information from the command line, but we'll focus on a PowerShell-centric one, our friend get-process. We know that if we run get-process without any options or flags, we get process information for each running process on the system. If you check out the column headings at the start of the output, you'll see things like npm-k values in this column represent the amount of non-paged memory the process is using, and the K stands for the unit, kilobytes. You can see Microsoft's documentation for a full write-up of each column in the next supplemental reading. This is useful, but it's a lot of information. It can be really helpful to filter down to just the data you're interested in. Let's say you wanted to just display the top 3 processes using the most CPU. You could write this command. Get-process pipe sort CPU descending pipe select dash first 3 dash property ID process name and CPU. And just like that, we get the top 3 CPU hogs on the system. This command might be a little hard to understand, so let's go through it step by step. First, we call the get-process commandlet to obtain all that process information from the operating system. Then, we use a pipe to connect the output of that command to the sort command. You might remember pipes from some Linux examples earlier. We sort the output of get-process by the CPU column, descending to put the biggest numbers first. Then, we pipe that information to the select command. Using select, we pick the first 3 rows from the output of sort and pick only the property ID, name, and CPU amount to display. Now that you've got some knowledge about both the command line and graphical tools Windows provides for investigating resource usage, Let's have a look at Linux resource monitoring. A useful command to find out what your system utilization looks like in real time is the top command. Top shows us the top processes that are using the most resources on our machine. We also get a quick snapshot of total tasks running or idle, CPU usage, memory usage, and more. One of the most common places to check when using the top command are these fields here, %CPU and %mem. This shows what CPU and memory usage a single task is taking up. To get out of the top command, just hit the Q key for quit. A common situation you might encounter is when a user's computer is running a little slow. It could be for lots of reasons, but one of the most common ones is the overuse of hardware resources. If you find that a top shows you a certain task is taking up a lot of memory or CPU, you should investigate what the process is doing. You might even terminate the process so that it gives back the resources it was using. Another useful tool for resource utilization is the uptime command. This command shows information about the current time, how long your system's been running, how many users are logged on, and what the load average of your machine is. From here we can see the current time is 16:43 or 4:43. Our system has been up for 5 hours and 8 minutes, and we have one user logged in. The part that we want to talk about here is the system load average. This shows the average CPU load in 1, 5, and 15-minute intervals. Load averages are an interesting metric to read. They become super useful when you need to see how your machine is doing over a certain period of time. We won't get into load averages here, but you should read about them in the next supplemental reading. Another command that you can use to help manage processes is the lsof command. Let's say you have a USB drive connected to your machine. You're working with some of the files on the machine. Then when you go to eject the USB drive, you get an error saying device or resource busy. You've already checked that none of the files on the USB drive are in use or opened anywhere. Or so you think. Using the lsof command, you don't have to wonder. It lists open files and what processes are using them. This command is great for tracking down those pesky processes that are holding open files. One last thing to call out about hardware utilization is that you can monitor it separately from processes. If you just wanted to see how your CPU or memory was doing, you could use various commands to check their output. This isn't immediately useful to see on a single machine, but maybe in the future, if you manage a fleet of machines, you might want to think about monitoring the hardware utilization for all of your machines at once. We won't discuss how to do this, but you can read more about it in the supplemental reading. You've done some really great work in this module. You learned a lot about how to read process information and manage processes, something that will be vital for you to know when troubleshooting issues as an IT support specialist. The next assessments will test you on that new process management knowledge. Then, drumroll please, we'll be on to the last and final lesson of this course. We'll cover some of the essential tools that are used in the role of an IT support specialist. You've made it all the way to the last module of this course. Great job! So far, you've learned how to navigate both the Windows and Linux operating systems, how to set up and manage users, along with how to manage software. You also learned how to work with disks and file systems, on top of working with processes and hardware resources. That's some seriously great work. The skills you learned in this course are essential for building a solid technical foundation as an IT support specialist. Now let's finish strong. In the next few lessons, we're going to wrap up the course with some of the more practical aspects of operating systems that you'll use all the time in IT support. Let's get started. In this lesson, we're going to talk about an important part of computing that makes working in IT support a little easier. Actually, it makes things a lot easier for just about anyone. Picture this. You're on your way to an important meeting. You've been rehearsing for this presentation all week, and now you're ready to show the bigwigs what you got. But wait, the slide deck, where is it? It's not on your laptop. Where could it be? It turns out you forgot your only copy on your desktop at home. It's too late now to turn around and get it, so you sit there, dreading the inevitable. But wait a minute. Suddenly, you remember that you have a remote connection set up from your laptop to your desktop. You use this connection to log into your computer at home, and just as if you were sitting at home, you're able to grab the file from your desktop and copy it to your laptop. You then proceed to give one amazing presentation. Consider another scenario. You bought a computer at a store and you're having a lot of issues with it. The store has a computer help desk that can help you with the issues, but it's after hours and the store's closed. You really need to get your computer issue fixed, so what are your options? Fortunately, the store provides 24/7 tech support online. Now, instead of waiting until a physical store is open again, you can reach a tech online and have them help you with your issue through a remote connection. Remote connection makes working in an IT support role much easier since it allows us to manage multiple machines from anywhere in the world. In this lesson, we're going to learn about remote connection. You've actually already been using it throughout this course. We've been using the Chrome Remote Desktop Connection to access our Windows Quick Labs, along with SSH or Secure Shell to securely log in to our Linux Quick Labs. But we're going to dig a little deeper in this lesson and talk about how remote connection works and the different methods to connect remotely to a machine. SSH or Secure Shell is a protocol implemented by other programs to securely access one computer from another. In the Quick Labs exercises, you've been using the Google Cloud Console SSH client to access the Linux VM instances. To use SSH, you need to have an SSH client installed on the computer you're connecting from, along with an SSH server on the computer you're trying to connect to. Keep in mind that when we say SSH server, we don't mean another physical machine that serves data. An SSH server is just software. On the remote machine, the SSH server is running as a background process. It constantly checks if a client is trying to connect to it, then will authenticate its request. The most popular program to use SSH with in Linux is the OpenSSH program. We'll be using it in this lesson, but we won't talk about how to install it just yet. We'll circle back to that in the next course, System Administration and IT Infrastructure Services. The same goes for Windows. We'll talk about how to use SSH from a Windows machine using the popular open source program PuTTY. For now, let's just talk about what happens when you use SSH. We're going to show you an example of SSHing into a remote machine. We already have an SSH client installed on this machine, but don't worry. We'll talk about the different SSH clients and installing them in the next course of the program, System Administration and IT Infrastructure Services. So first things first, to log into a remote machine, we have to have an account on that computer. We also need the hostname or IP address of that computer. Let's test this. So SSH Cindy at IP address. We get this message, the authenticity of host and then the IP address can't be established. This message is just saying we've never connected to this machine before and our SSH client can't really verify we're connecting to a machine we want to connect to. But we can verify this is the right machine, so let's just go ahead and type yes. Now, this host gets saved to the computer as a known host, so we won't get this message again when we try to log into it. Okay, now that we're connected through SSH, any of the text commands that we type are sent securely to the SSH server. From here, you can even launch an application that'll let you see a GUI instead of working directly in the shell. You can read more about how to do that in the supplemental reading. We can connect to SSH using passwords, as you saw earlier. This way of authenticating to a remote machine is pretty standard, but it's not super secure. The alternative is using an SSH authentication key. SSH keys come in a set of two keys called private and public keys. You can think of them as actual physical keys to a special safe. You can use one key to lock the safe, but it won't unlock it. The other key can then only unlock the safe, but not lock it. That's basically how public and private keys work. You can lock something with a public key, but you can only unlock it with a private key and vice versa. This ensures that whatever is in the safe is available to only those with the public and private keys. You'll learn about the technical details of public and private keys in our IT security course. Don't worry if this doesn't make sense right now. It will. And that's basically how SSH works. Not too scary, right? Another way that you can connect securely to a remote machine is through a VPN. A VPN is a virtual private network. It allows you to connect to a private network, like your work network, over the internet. Think of it as a more sophisticated SSH with a lot more setup. It allows you to access resources like shared file servers and network devices as if you are connected to your work network. Spoiler alert, we'll also touch upon the technical details behind VPN in the IT security course. We've covered a lot about remote connections and how they work. We'll talk more about the popular remote connection programs for Windows and Linux and how to set them up in the System Administration course. The ability to make remote connections is equally useful on Windows computers, but there isn't an open SSH client for the Windows OS. At least not yet. That's changing though. Microsoft has announced that they'll be contributing to the Open SSH project to provide an integration with PowerShell. You can read the full text of their statement in the supplemental reading that's included after this lesson. It's great to know that Windows will eventually integrate an Open SSH client into PowerShell. In the meantime, what's an IT support specialist to do if they want to SSH into another computer? Well, there are a host of third-party applications that can serve as SSH clients on Windows. Let's take a look at one of the more popular tools, PuTTY. PuTTY is a free, open-source software that you can use to make remote connections through several network protocols, including SSH. You can visit the PuTTY website to download the entire software package with a Microsoft installer. Those are the MSI files we talked about earlier. Or you can choose a specific executable which provides the functionality you're after, like putty.exe. The PuTTY downloads page is linked in the next supplemental reading in case you want to check it out. Once you've downloaded and installed PuTTY, you can use it by launching the GUI. A window will appear showing you the basic options for your connection. Make a note of the hostname, port, and connection type options. By default, the port is set to 22, which is the default port the SSH protocol uses, and the connection type is set to SSH. All you need to do is type in the hostname or IP address of the computer you want to connect to. Then click Open to start up a new SSH session. And now I've SSH'd into a remote computer. Running PuTTY from the GUI isn't your only option. You can also use it on the command line. Open a PowerShell prompt and type out the application name like this. Then tell it you want to connect via SSH by adding the -SSH option. You can also provide the user and address in the form of user@IP address and specifying the port at the end. Altogether, the command would look something like this. PuTTY also comes with a tool called Plink, or PuTTY Link, which is built into the command line after PuTTY is installed. You can use Plink to make remote SSH connections too. SSH can be super useful, especially if you want to connect from a computer running Windows to a Linux-based operating system running remotely. Microsoft actually provides another way to connect to other Windows computers called the Remote Desktop Protocol, or RDP. There are also RDP clients for Linux and OS X too, like RealVNC and Microsoft RDP on Mac. We'll add some links to these clients in the supplemental reading. RDP provides users with a graphical user interface to remote computers, provided the remote computer has enabled incoming RDP connections. A client program called the Microsoft Terminal Services Client, or MSTSC.exe, is used to create RDP connections to remote computers. You can enable remote connections on your computer by opening up the Start menu, right-clicking on This PC, then selecting Properties. From there, select Remote Settings. And then pick an option from the Remote Desktop portion of the panel. There are some security implications that come with allowing people to remotely connect to your computer. You should only let users who you trust do this. Typically, in an industry setting, these kinds of settings are usually set by the system administrator for the company's computers that connect to the network. Once you've allowed connections on the remote computer, and provided you're on the list of users allowed to access it, you can use the Remote Desktop Protocol Client, mstsc.exe, to connect to it from anywhere else on the network. You can launch the RDP client in a few ways. You can type mstsc at the run box or look up Remote Desktop Connections in the Start menu. Once you've launched the client, it'll ask for the name or IP address of the computer you want to connect to. The Windows RDP client can also be launched from the command line, where you can specify more parameters like /admin if you want to connect to the remote machine with administrative credentials. You may have already used the Windows RDP client in Quick Labs, but if you haven't, we've linked to the RDP documentation in the supplementary reading in case you want to learn more. Have you ever tried sending a file over to a coworker? What methods do you use? Do you attach it to an email and send it? Or do you copy the file to a USB drive and then transfer the file that way? There are lots of ways to transfer files. In this lesson, we're going to talk about a method that uses remote connection. SCP, or Secure Copy, is a command you can use in Linux to copy files between computers on a network. It utilizes SSH to transfer the data. So just like you would SSH into a machine, you can send a file that way. Let's see this in action. Let's say we want to copy over a file from our computer to another computer. To do this, we can run the scp command with a few flags. So scp desktop, my file, over to Cindy at In this command, we run the scp command with the path of the file we want to transfer to the user account, hostname, and path of where we want to copy the file to. Now it prompts us for the login information of the computer we want to send the file to. After we enter this, we can verify that the file is successfully copied over. Yep, there it is. The scp command is a super useful tool if you need to copy files to and from computers in a network. You can read more about the command by checking out the man page. How can we share files and data over the network on a Windows computer? Well, it just so happens that the PuTTY program we talked about a couple lessons back supports the SCP protocol. The PuTTY package comes with a tool called the PuTTY Secure Copy Client, or pscp.exe. You can use it to copy files in a very similar way to the Linux scp command. Let's take a look. pscp.exe, and I'm going to grab a file from my desktop. Then I'm going to copy it to my Linux workstation. And then I'm going to add the location of where I want to copy it to. Now if you go back to my Linux workstation, we can see that it was copied. Using PuTTY or SCP to transfer files can be a little time-consuming, especially if you need to transfer files to multiple machines. As an alternative, Windows came up with a built-in mechanism to share files by using the concept of shared folders. Shared folders do pretty much what you'd expect from their name. You tell Windows you want to share a folder with a person or group of people, then drop some files into it. Anyone you've shared the folder with can then access those files. Sharing folders in Windows is easy. Just right-click on the folder you want to share, then mouse over the Share With option, and then pick specific people from here. From here, you can add the individual users or groups you want to share the folder with. There's even an option to add everyone to the sharing permissions, which might be convenient, but isn't super secure. Once you've shared the folder, you can access it from other computers. Start by opening up this PC, then going to the Computer tab, and from here, you can map the folder directly to your computer with the Map Network Drive option. Finally, on another computer, you can visit it directly from the Run box by typing in / whatever the computer name is, and then / the folder name that you mapped it to. You might be interested to know that you can share folders from the command line too, using the net share command. Net share lets you do the same thing as the GUI sharing workflow, and you'll need to specify what kind of permissions you'd like to give which users. Let's say you wanted to give everyone on your network full permissions to a folder called Share Me. You could execute this command from an elevated or administrator level PowerShell prompt. Net share me users. /grant everyone full. Users will be able to access the shared folder by using the same methods we talked about before. The net share command can also be used to list the currently shared folders on your computer by executing it without any arguments. If you'd like more information on net share and its abilities, check out the documentation in the supplemental reading. We've talked a little bit about virtual machines before. We've also been using virtual machines throughout the Quick Lab assessments. In this lesson, you're going to learn how to install, manage, and remove a virtual instance. A virtual instance is just a single virtual machine. We're going to be using the popular open source virtualization software, VirtualBox, to manage virtual instances. You'll find a link to download VirtualBox in the reading right after this lesson. I'm currently using a Windows machine, and in this lesson, we're going to set up and virtualize an Ubuntu instance. I've already installed VirtualBox on my machine, so let's go ahead and launch this application. We won't go through all the menu items for VirtualBox, but we'll talk about some of the main ones. First up, how do we install a virtual instance? I've already pre-downloaded an image of Ubuntu from their website and saved it onto my desktop, but I have to install it somehow. Well, to install this, I'm just going to click this New button here to create a new VM. I'm going to give my VM a name and select the type and version of my OS. I'm just going to stick with the defaults. Next, it asks how much RAM I want to dedicate to this VM. 1 GB is more than enough for me, so I'm just going to keep this and then continue. Now it asks how much hard drive space I want to dedicate to this VM. I'm just going to keep the default of 10 GB and click Create. We're going to keep the default values here and just skip through to the Create. Awesome. You can read more about these options in the supplemental reading. Now in my menu here, I can click Start, and it'll start the VM. It'll prompt me to select a media to launch from, similar to booting a USB drive with the OS image on it. So I'm just going to select the image I downloaded. And from here, the installation starts up. That's pretty much it. Okay, what if we decide we want to use more than 1 GB for the OS? On a physical machine, we'd have to buy more RAM and install it, but since we're using a VM, it's as easy as changing a setting. To modify hardware resource allocation to a VM, all we need to do is right-click on the VM, then click Settings. From here, we'll be able to change how much RAM we want along with other settings. We won't discuss the specifics of these settings, but you can see how simple it is to modify a VM instance. Now, what if we decide we don't want to use this VM anymore? If this was a physical machine, we'd have to worry about where to store or recycle the hardware. For virtual machines, though, all we need to do is right-click and select Remove. From here, it asks if we want to remove all files, including the VM install itself, or just remove it from the list of VMs. Let's go ahead and delete all files. And that's it in a nutshell. Super simple. If you want to learn more about how to use VirtualBox or other virtualization software, don't forget to check out the supplemental reading. Remember from the first course in our program, Technical Support Fundamentals, that we introduced the concept of logs? A log is like your computer's diary. It records events that happen on your system. What kind of events? Well, pretty much everything, like when your system shuts down, when it starts up, when a driver is loaded, when someone logs in. All of these things can be written to a log. It's also written with a lot of detail. Logs tell you the exact time that an event occurred, who caused the event, and more. We'll be looking into some sample log snippets in the upcoming lessons to get a better sense of how to read one. The act of creating log events is called logging. Your system does a pretty good job of logging events right out of the box. In most systems, there's a service that runs in the background and constantly writes events to logs. These systems are customizable so you can log any specific field you want, but by default, it logs all the essentials. By the end of this lesson, you'll learn where all the important logs are kept on the Windows and Linux OSs. You'll also learn how to read a log and utilize common troubleshooting practices when it comes to logs. When you're working in IT support, you'll need to gather as much data as you can to troubleshoot an issue. Logs tell us important things like errors that occurred, changes that were made, etc. They are a reliable source of information. Similar to how we can jot down our life events in a journal, events are also logged on our machines. In Windows, the events logged by the operating system are stored in an application called the Event Viewer. Whether you're trying to figure out why a computer game keeps crashing, or troubleshooting login or access problems, or just satisfying your curiosity about what's going on in your system, the Event Viewer is a great first stop. Let's take a look at some of the information it collects, and how you can use the Event Viewer to get answers you're looking for. You can launch the Event Viewer either from the Start menu or by typing in eventvwr.msc from the Run box. The default view the Event Viewer shows is a summary of potentially important recent events. In our case, this isn't super interesting since we're more concerned with any issues that occurred. Instead, let's take a look at the left-hand pane, where we can see a few different event groupings. The first group we see is called Custom Views. The Event Viewer records a lot of information about the system, so it can sometimes be a little difficult to tease out the signal, like recent events, from the noise or the stuff you don't care about. This is where the concept of custom views comes in handy. With a custom view, you can create a filter that will look across all the event logs the Event Viewer knows about and tease out just the information you're interested in. Let's say we wanted to only see events of error, severity, or higher that were logged in the last hour. To do this, click on the Create Custom View option in the right-hand Actions pane. This will bring up a tab called Filter. From there, click the Error and Critical checkboxes. We're going to change the Logged drop-down menu to the last hour, and the event logs we're going to select are just the Windows logs. Then click OK. Then we're going to give our view a new name. Click OK once more. Once you're done, you'll see a new view come up under Custom Menus, where only the events that matched your filter are displayed. The other two categories of logs you'll see in the left-hand navigation page are Windows logs and Application and Services. The Windows logs categories contain event logs that are generally applied to the whole operating system. Let's say you're having an issue with a driver failing during startup. The log called System would be a good place to start. If you want to see who's been accessing the computer, then you begin investigating the security log. The other category is called Applications and Services logs. This category contains logs that track events from a single application or operating system component instead of the system-wide events of the Windows logs category. For example, if you were having trouble with PowerShell and wanted to get more information about it, checking out the PowerShell log under Applications and Services logs would be a great first step. Regardless of its category, each line in a given log in the event viewer represents an event. Each event contains information grouped in columns about the event, like the logging level. Information is the lowest level, and critical is the highest. You can also find the date and time the event occurred. Selecting an event will bring up more detailed information in the bottom pane of the event viewer. This can help you dig into troubleshooting or even give you context for a bug report. The event viewer is a super helpful tool for IT support specialists. It can provide you with a lot of really detailed information about the problems any software or hardware might be experiencing on your system. There's a lot of information in there though, so don't forget about its custom views and filtering capabilities. More importantly, don't hesitate to poke around the tool and get used to finding things in its interface. You'll have fun and you'll learn a lot. Next up, the wild world of Linux logs. Logs in Linux are stored in the /var/log directory. Remember that /var directory stands for variable, meaning files that constantly change are kept in this directory. And it turns out that logs are constantly changing. If we look at the /var/log directory with an ls, it might seem a little intimidating. Don't worry, each of these log files stores specific information that we can figure out by their file names. Let's check out some of the common ones you'll look at. /var/log/auth.log. Authorization and security-related events are logged here. /var/log/kern.log. Kernel messages are logged here. /var/log/dmessage. System startup messages are logged here. If you encounter an issue at, let's say, boot up, this is a good place to check for information. It might get a little tiresome to open up each of these log files to find information about events. Luckily, there are also log files that combine the information of other log files. The downside is that these files are usually very large. If you have a pretty good idea of where a problem might lie, you might want to opt for the smaller and more specific log file. The one log file that logs pretty much everything on your system is the /var/log/syslog file. The only thing that syslog doesn't log by default are auth events. When troubleshooting issues with user machines, /var/log/syslog will usually contain the most comprehensive information about your system. So that should be your first stop. Log files output a lot of events. By that logic, they take up a lot of data that has to be stored on our machine somewhere. We generally just want to see the latest events on our system, so we don't need to overload our disk with all this information. Luckily, our systems also do a good job of cleaning out log files to make room for new ones. They use something called log rotation to do this. In Linux, the utility to rotate logs is called log rotate. You might want to investigate an event that happened a month ago, so you can change your log rotation settings to make sure not to delete events that are that old. We won't discuss how to work with log rotation, but you can read more about it in the supplemental reading. We've talked about logging in the context of a single machine, But if you find yourself managing many systems and want to be able to parse their logs in one central location, you can use something called centralized logging. We won't talk about how to do this, but if you're interested in setting up a centralized server, check out the next supplemental reading. Okay, enough talk about what logs are. Let's actually look at some real ones. Whoa, this looks super intimidating, but don't worry. We're not going to be reading all of this. In the next lesson, we'll teach you how to troubleshoot using logs, but for now, let's just read one line in syslog and parse what it says. The first field here is the timestamp when the event occurred. Pretty straightforward. But depending on the log, you might see a time format you aren't familiar with, like a long string of numbers such as 150-153-8594. Timestamps found in a format like this are referred to as Unix or epoch time. At first, you might be baffled by this. Why would you represent time in this way? And just what exactly is the Unix epoch? The Unix epoch time is used to represent then. It's the number of seconds since midnight on January 1st, 1970, a sort of 0 hour for Unix-based computers to anchor their concept of time. This means that 150-153-8594 represents the date time Monday, July 31st, 3:03:14 Pacific Standard Time. Why midnight on January 1st, 1970? Is that date the birthday of Unix, or does it mark some other significant event? The actual answer is much simpler. The original engineers of Unix at Bell Labs just picked it because it was convenient. So don't be caught off guard if you see a timestamp like this. The next field is the hostname of the machine the event occurred on. Next up is the service that the log event is referring to. And last is the event that occurred. In the next lesson, we'll show you some common troubleshooting tactics when using logs. Yes, now you've made it to the really fun stuff. Let's use the information we learned about logs to actually investigate system issues. Take this scenario. You're working in an IT support role, and one of your users tells you that they leave their computer on all the time. But they recently woke up to find that the computer had shut down. What do? Maybe you stay up through the night, keeping a close eye on the computer, not taking any breaks to use the restroom or even blink. You wait and wait and wait until the computer shuts off. Or, in a sane and normal world, you decide to just look through the system logs. Let's go with that option. So where do you begin? At first, logs can be really messy and daunting to look at. We'll talk about the techniques you can use to view logs, but rest assured, you'll never need to read a log line by line. Whew. The first thing you want to do when looking at a log is to search for something specific. But what if you're seeing issues with an application and you don't know where to start looking? Well, luckily for us, our systems log information in a pretty standard way. If an application is getting a lot of errors, what do you think you can search for? That's right, the word error. What if you're seeing an issue with a specific application? What else do you think you can search for? If you guess the application name, you're right. You've already been able to filter out your logs to look for specific things that you might be seeing. Let's see this in action. Here, we can see the log results that have the word error in them. If you need to investigate issues that happen around a certain time, you can actually do that by checking the timestamps around that time. You may find the problem that's causing your issue this way, or at least get a little closer to figuring out what it is. When you finally get to a juicy log portion that might help you uncover problems, you usually want to start looking at the output from either the top or bottom. Let's say you're seeing lots of errors. Each of these errors could be happening because of a root issue. If you resolve the root issue, you'll fix the cascading errors. Take a look at this. The log is riddled with errors, but if we scroll up, we can see the one error that spun up all these others. If we fix that, then the other issues will most likely be fixed. On the flip side, if you aren't seeing any indicators of a problem in a log, you might want to work from the bottom until you come across a clue. Your system could be functioning normally, but when you scroll down to read the output, you see a log entry that may be related to your problem. Another troubleshooting tactic you can use with logs is to check them in real time. Let's say every time you launch a specific application, it does something abrupt and shuts off. Sure, you can check the logs in post and keep track of your time, or you can look at the logs in real time. To do this, we can use one of the commands we learned in a very early lesson, tail. Let's take a look at what this means. We're going to tail-f the syslog file and keep it in an open window. Then, we're going to turn off Bluetooth to show you the events it's logging. Now we can see Bluetooth logging data in real time. Look at that! We've come full circle. I told you those commands would come in handy. Using these simple log tactics will help you throughout your career as an IT support specialist. You've certainly covered a lot so far. Now you've picked up how to troubleshoot using logs too. Logs will be one of your best friends when you're faced with a problem machine that leaves no obvious clues. Talk to the logs and listen to what that sweet, sweet log voice is telling you. You'll discover the problem in no time. We learned how to install an operating system for ourselves. But when you work in an IT support role, you have to install operating systems for everyone else. Installing an operating system with a single USB stick, like we did in the very early lessons of this program, can get extremely time-consuming, especially when you need to do it for lots of machines. Fortunately, in the IT world, we use fantastic tools to make our jobs easier. Remember that imaging a machine means to format a machine with an image of another machine. This includes everything, from the operating system to the settings. In this lesson, we're going to briefly touch upon some of the options you can use to image machines and help deploy your operating systems a little easier. One tool we can use to image a computer is a disk cloning tool. It makes a copy of an entire disk and allows you to back up a current machine or set up a new one. There are lots of disk cloning tools out there to help you complete this task. The benefit of disk cloning over a standalone installation media is that you can also install settings and folders that you might need. One of the many disk cloning tools out there is the open source software CloneZilla. It can be used to back up and restore a single machine or many machines simultaneously. A popular commercial imaging tool is Semantic Ghost. To read more about other disk cloning software, check out the supplemental reading right after this video. With disk imaging, lots of tools offer different ways you can clone a disk. One option is disk-to-disk cloning, where you connect an external hard drive to the machine you want to clone. You can connect a hard drive, like your HDDs and SSDs, into something known as an external hard drive dock. These devices are great IT tools that kind of look like toasters. Once you connect your external hard drive, you can use any disk cloning tool of your choice. We're going to show you a really quick example of how disk cloning works. Let's use the Linux command line tool dd to copy files. dd is a lightweight tool that's also used to clone a drive. Again, you can use any tools you want to clone your disks, but right now we're just going to use dd. Let's make a copy of the USB drive I have connected in my laptop, then save it as an image file. First, we want to make sure we have this drive unmounted. Then we want to run dd. You don't have to know how dd works to use this command. Actually, you should check out the final supplemental reading to learn more about this tool. This just says I'm going to copy the contents of /dev/sdd, which is the USB drive, and save it to the desktop in an image file. Once the image file is saved, if we open it up, we should see the exact same contents as the USB drive. You can use DD for larger disks like hard drives and it'll function the same way. Pretty cool, right? Another method you can use to image a machine is to request the images directly from the network. Lots of operating system manufacturers today offer network-initiated deployments. This means no more messy standalone installation media. Instead, you can just download and install an operating system through the network. If you want to use your own images and not the built-in network boot options for your computers, there are other options for that too. We don't discuss the specifics of them here, but they require a bit of automation to get going. That means you'd have to utilize scripts. And we won't discuss how to do that in this course, but you can be on the lookout for it in Course 5 on IT automation. It doesn't matter if it's a laptop, desktop, Windows OS, Linux OS, etc. If you're managing the operating system deployment for a company, you'll want to keep some aspects of hardware standardization in mind. Imagine if your company has a different laptop with different drivers that needed to be installed. This can get tedious to maintain. It's usually a good idea to try and standardize what type of hardware you use in a company to make your job of deploying operating systems a little easier. Okay, you're so close to finishing this course. We've got a final pair of assessments for you, where you'll use logs to help you track down some issues. Wow, amazing work! You've covered a ton of information in this course. You learned how to navigate the Windows and Linux OSs, how the intricate components of an OS work, and how to troubleshoot common issues found within them. You also learned how to manage software from basic device drivers to applications, set up disks and partitions, format a file system, read logs and traverse them. Finally, you've picked up some skills on how to make your job easier using remote connections and operating system imaging. You've accomplished a lot and should be incredibly proud. The skills you've learned in this course will follow you throughout your IT career. After all, the OS is the component that you deal with the most. In the next course, we're going to kick it up a notch and show you how to work with operating systems at a larger scale. You're going to use the skills you learned in this course that helped you manage one machine to jumpstart your learning for the next course. That's where we'll teach you how to manage a whole fleet of machines. So it's time for me to say so long. It's been a blast being your guide to operating systems and sharing my passion for OSs with you. Your next course, System Administration and IT Infrastructure Services, is being taught by my friend and colleague of mine, Devon Shri Theron. Tell him I said hi.